Recording in progress.
Okay, we didn't miss much. Okay, so again, a semiconductor looks like that, and it only works when current flows in the forward direction, and this is called the cathode. And the band looks like this. That's the cathode side, which is the negative side, the plus and the minus. And we have our incoming AC that goes into here, and since this is plus and minus, uh, what we end up with is something that looks just like this. Whoops. And goes only positive on this side, and that is our DC. So again, a semiconductor is useful. A diode is useful because it generates AC. It generates DC from AC, and we have a special kind of diode that does that. That lights up when it's forward biased, when we have current flowing through it, through the one-way sign. If it's going in that direction, we get this thing called light, and that's known as a light-emitting diode. Okay.
So, Scott, just
Yep.
to make sure I got it right, both diodes, semiconductors, and even the vacuum tubes, their sole purpose is to convert AC to DC?
No,
Okay.
they happen to do it very well, but no, I mean, that's one of the main things that they are used for. You could not build a power supply very easily without one.
Okay.
But
And
we're
are they the same as a transistor too?
we're getting
Or
there right now.
okay.
Okay, so we just did our diode, which is a two-terminal device. I'm going to erase these for now. All right, so a diode is a two-terminal device. It has instead of some intrinsic silicon, which is uh, essentially the outer shell, has one, two, three, four electrons and four not electrons, so it's got spaces for four. By adding or subtracting one to it, by either adding one or subtracting one, what we've done is we've taken it and gone from basic silicon, which is neither a conductor nor an insulator, and converted it into something that conducts a little better or a little bit worse. And by sandwiching two pieces together, for instance, we can do an N and a P, and we can go like this and run current into it and actually have current flow in one direction when we put a voltage on it. And again, a silicon diode is about 0.7 volts. A germanium diode is about 0.3 to make it work. Okay, so this is a diode. It's like a one-way street sign or a traffic cop always pointing in one direction. But now we're going to take this diode and we're going to take two of them and we're going to sandwich them back to back. And we're going to organize them in a vertical format like this. And we're going to go NP. So we're going to have an NP junction right there. And then we're going to have a little more P, and we're going to have an N. So really what this means is we can get rid of the dividing line like that, and we can get rid of the letter P. And now notice we have three letters. N, P, N. All right, so this is N material, this is P material, and this is N material. So they're silicon, which has been altered in a way using either like phosphorus or boron or something like that, that makes it behave more like a positive or more like a negative. Okay, so now what we can do with this is we can say, okay, well, this PN, if we put a voltage right here, like 0.7, and put this at 0 volts, 0 volts is known as our ground. If we can put a little bit of voltage there, we end up with a current that flows in the direction of the arrow. What that does is say if we were to put a power source up here, which is a plus something like 24 volts, what would happen is we would get an avalanche of current, much, much, much more available to us than anything we would ever get on that very first little arrow. So this little arrow right here indicates kind of like the driving signal, and this avalanche indicates what can actually come through from somewhere else. So this is from a different source.
But that's going from N to P?
It goes from N to P, but then back to N.
I thought it only goes one direction.
It does, but it takes, in other words, because this is a forward biased junction between this P and N, once it can overcome the N, it basically follows and flows through the entire path.
So it goes from N to P.
It's
It's supposed
it does, but the pull of the other side is bigger for it. In other words, it sort of like opens up the path. It opens up the
So
entire path. I
to
mean,
have my
if you were to just look at it like this, then it wouldn't work, right?
but the P also has this 0.7 coming in there. What is that?
That's a biasing voltage. In other words, if that basically looks at it like this and says, okay, here's this diode right here,
okay.
and I'm going to forward bias that diode, but then sandwiched onto it is this other thing, this other N. And what that's going to do is that's going to say, okay, if there's a sufficient voltage there, or in this case, it actually could be negative, what'll happen is we end up going and generating a much larger current available. If there's more current available, then we're going to allow a huge current to flow through.
So the diode's supposed to go from P to N if it has a voltage difference from the P side, correct?
Correct. It will
Okay.
basically turn on.
Okay.
And in doing so, in a transistor, this is known as a transistor, you end up with current flowing from this side, which is actually called the collector. This side is known as the emitter, and this is known as the base. You end up with a large amount of current flowing from the collector to the emitter. And what's significant about this is, let's say that I limit the voltage and current available at the base using a resistor. So what that ends up doing is it makes a proportional copy of the amount of current flowing from the base to the emitter. It makes a proportional copy from the collector to the emitter. Chuck, remember you were asking something about amplifiers? Chuck, you're muted.
Yes, this is exactly it. Yes, I
Okay.
was thinking of a switch that would turn on and off and allow a greater current to go through than
Yep.
what the source was. Yes.
Okay, this is the basis of amplification right here in our modern world. Because if we were to draw a relationship between input and output signals, so let's draw our input, and here's our output. It would look something like this. Okay, so at some point, we have our turn on voltage, turn on current. In other words, up until this point, the whole transistor doesn't do anything. above a certain point, it doesn't matter how much more we put in. The thing is, the transistor is putting out as much as it possibly can. In other words, that channel, that collector to emitter channel is completely full. Which means, you can put in more input, all you'll be doing is heating the thing up. You'll be just basically adding nothing else to it.
So the resistor slows it down.
The resistor limits the amount of current that flows.
Okay. And
And
the
also-
transistor makes it go.
Well, basically it's yeah, I mean basically you probably have a little bit of a resistor in here too, just to protect things from complete overload.
Okay.
But notice that we have 3 distinctly different regions of operation. Well, this one's called cutoff, when the transistor doesn't work. And really, it's very flat. And then it suddenly starts working. So how about this thing right here? In between, let's say, here and here, what does that look like?
Increase.
Yeah, but what does it look like? It's almost a perfectly straight what?
Linear.
Yep. That would be known as the linear region. And over here would be called saturation. In other words, no matter how much more we put in, we don't get any more output. So, if we are trying to just have a switch that we turn something on and it makes something happen on the other side, and we don't really care if it's clean or not, we just want to turn on a light bulb. It's fine to operate in saturation. How about if we're trying to take a small signal, let's say somebody's voice, and make a bigger copy of it? So we'll say it's voice times 100. What region of this would we want to use?
Straight area.
The straight area, the linear region. That is why we have something called a linear amplifier. Because the transistor is the basis of amplification in the modern world. And because we actually want something to be clean and distortion free, we want to say if something is low, then we want the output to be low. And if something is high, we want the output to be proportionally large. So we basically say, okay, this is our valid input range right here for our microphone. And this is what's driving our loudspeaker. Notice it's a lot bigger than what's driving than the microphone. This can be on the order of 100 or 200 times from a single transistor. Typically, we'll dial it back a little bit so that it'll, let's say, be 10 or 20 times. But now, this is where it gets really cool. How about if I do this? So this transistor actually is drawn like this. They're still the same thing. There's my base, there's my emitter, there's my collector. Okay, this is a 3-terminal device. If I have a small signal that goes this way, I have a very, very big signal that goes this way, which is a big copy, assuming I'm operating in the linear region. Now, is there any reason that I couldn't take the small signal that's being generated, that's generating the big signal, and then take the big signal and do this with it and run it through an even bigger transistor? Can anyone think of any reason why I couldn't do that? I can do anything I want so long as the device is big enough. And this is actually called cascading amplifiers. So let's say I have a gain of 20 times right here, and I have a gain of 20 times right here. What would be the overall gain?
40.
That'd be 400 times.
400. Oh yeah.
This kind of thing is used all the time to make really, 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 really big copies. So you basically take something, you make a small copy of a small copy of a really small thing, and then you make a big copy of the small copy. So this would be cascading amplifiers.
What do you mean copy?
Well, let's say that I have this. Let's say that I have a picture of a smiley face, right? And I take a small smiley face and I make a big copy of of that small smiley face.
Well, that's a big copy.
Big copy. Now I take that and I make a bigger copy.
Arr.
Right? Is each one identical to the previous one? I don't think so. Not
No.
quite, because they're copies. That's exactly what an amplifier does. An amplifier does not make something bigger. It makes a large copy of something small.
Okay.
And that's why if you're using amplifiers, it's important to know about something called distortion, because every time you make a copy of something, the quality of the amplifier that you're using creates distortion. And distortion will cause something on the output to not quite look like something on the input. That might be that, oh look, the eye's a little bit funky on this one. And look, we couldn't even fit that whole thing on the right-hand side. So distortion is the difference between one copy and the next copy.
And that means that the amplifier in there is needed so much because the electrical signal inside of a antenna is very, very low. It's very small
So
current, right?
Let's do this. Well, it's a very small current and very small voltage. Typically, this will be on the order of 0.0000000001 volts.
That's an antenna.
Coming off the antenna. That's a picture of an antenna.
Mm-hmm.
So how do you amplify that into something? How do you amplify that into something that you can actually hear audibly?
Yeah, that'll run a speaker or something.
And you have, to run a speaker, and you basically have this amplifier stage right here. And then once you do that, you'll typically run this through a mixer, which will combine it with another frequency, and then that will also serve as the basis for another amplifier. And then you'll also have a filter thrown in right there. And then maybe after the amplifier, you'll run it through another mixer with another local frequency. And then you'll run that through another filter. And then you'll run that through a product detector like that. And then you'll use that through another amplifier to power your speaker.
Wow.
That's
So-
what
so-
happens.
So what's the PD?
A product detector, but you don't need to know that yet.
Okay.
Okay.
Essentially, it's
So I know it was explained that a mixer takes two currents and fixes one so that it becomes a third, but I don't really understand what that means.
okay.
So for example, in this, what is the mixer doing?
Okay, so a mixer. So we're operating in the frequency realm. So let's say we have a signal of 1 megahertz coming in off of the antenna. And a proper drawing for a mixer is a letter X. A mixer is a non-linear device, which is, let's say we have something that's at 9 megahertz. We have an oscillator, which is again built of capacitor and inductor operating at certain frequencies, usually with a transistor as an amplifier operating in feedback, creating positive feedback. And we have picked a frequency of 9 megahertz to make. So what a mixer does is it takes input frequencies and it generates sum and difference frequencies. So this will generate 9 minus 1, 9 plus 1, 2 times 9, 2 times 1, and it'll do 2 times 9 plus 1, and 2 times 9 minus 1, and 9 plus 2 times 1, and so on and so forth. It'll make just a mess of stuff. Typically, what comes out of a mixer is a very big combination of frequencies. So if I had on a frequency chart, so 0 up to infinity, if I had 1 megahertz right here and 9 megahertz here, and those were both going in, the stuff that would be coming out would be like this. There'd be frequency spikes all over the place. Well, I know that I want this, for instance, 9 plus 1, which is 10. So how would I go about trapping those? I would build myself a filter with a center frequency of 10 megahertz. And how do you build a filter? What are the two things that are used to build a filter? We talked about them yesterday. One is a capacitor, and the other one is
Inductor.
inductor. Those are frequency dependent components. And by putting them in the right order, I can create something that has a frequency response that looks like this, which filters out just the frequencies that I'm looking for. This is the basis of how every radio works. This is the basis of how your stereo works. This is the basis of, if you've ever seen a graphic equalizer, if you've ever seen a speaker that had 3 different speakers. There was a woofer and a tweeter and a mid-range. This is the basis of something called a crossover network that allows, because what's the point of taking that tiny little speaker and sending your subwoofer sounds to it? It's not going to do anything. What's the purpose of sending your tweeter and your tweeter sounds to your subwoofer that's sitting on the back window of your car? The answer is there's no point. So by using things that look like that, capacitors and inductors, we can make a frequency sensitive filter that allows us to just send frequencies that we care about to places we care about. All right. We digressed a little bit, but that was a good digression. Okay, so that's a transistor. Another form of a transistor looks like this. All right, remember the first one looked like this. All right, everything is connected. But what do you notice about this guy right here? What do you see right there? What does it look like to you guys?
Capacitor.
Looks like a capacitor. And a capacitor is just 2 metal plates with a space in between. That's exactly what this is. It generates an electric field. This is actually known as a field effect transistor. This one over here is a bipolar junction transistor. There's actually a physical junction. The one on the left is known as a field effect transistor. And again, it's a field because there's a gap in between, and in between those 2 plates, there's an electric field. Now, the electric field, when it gets charged up plus, for instance, will allow this channel to open. When it goes away, it allows the channel to close, and the channel closes up. So by altering the voltage instead of the current, what we've done is we have generated a device that creates a copy in current of a voltage. And because there is no leakage across this junction right here, because it's a capacitor, it uses very, 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 very low power, especially when there are, let's say, 1 billion of them on a chip, which you'll find in your phone. What do you think? Is it better if your phone operates the way that it does, or is it better if your phone generates a lot of heat and you can't hold it after 30 seconds? Because that's the difference. The other thing is that it would use up its battery in 10 minutes instead of 10 hours. That's why field effect transistors are really important. Okay, next thing we're going to do is schematics. A schematic is basically a picture of how things are connected electrically. So the first one we're going to do is something like this. Whoop, there's a transistor, and here's a light bulb, and here's a battery. All right, so we are going to show this is a ground. We could also do a ground that looks like that. Ground is the same thing no matter what it looks like. Ground is our 0 volt reference. It can be drawn a whole bunch of different ways. Okay, so this is a very interesting little circuit because this is our lamp and this is our transistor, and on the input right here, what we're going to do is separate our transistor like that. Okay, so knowing what we know, considering that this is a diode right here, this half of the transistor, when our voltage goes positive here and negative here, what happens to that diode?
It activates.
It activates.
It allows flow. Yeah.
Right, it activates. And what happens is that when it activates, we are allowed to deliver power, current, through that path. When that happens, we get current that flows from this battery through the lamp, down through the transistor to ground. The act of doing that makes the lamp turn on. When we take that away, what happens to the diode?
Goes off.
It goes off. Okay, when the diode goes off, what happens to that path from the lamp down through the whole transistor?
Is it open?
It's closed. I mean, it becomes an open circuit. The path is closed, it's no longer available, and the lamp turns off. So what do we have here? We have an electronic light switch.
Okay, Scott,
Yep.
looking at the resistor
Uh-huh.
and what's happening there? It seems like that's completely irrelevant.
Oh, no, it's completely relevant. Let me ask a question. So we're going to get rid of this. Now, I'm just going to draw a diode. In fact, let's just draw a diode. And we're going to hook it up to a battery. Here we go. And here's our ground. Okay. What will this circuit do?
Activate with the same voltage as the battery.
To activate with the same voltage as the battery. So what if this is a 9-volt battery? Well, this will see 9 volts. This will see 0 volts on this side. Will the diode work? Yeah, right? Because this is plus and this is minus. So the diode will work, right? For a very, very, very short time. And why will it work for a very short time?
It'll burn.
Power
current
has
is-
to go somewhere, and a diode is once it turns on, it's on, right? It basically activates very much like a short circuit. So once this can be replaced by a short circuit, ready? We're going to do some quick math, everybody. We're going to do Ohm's law. Here we go. E equals I times R. What is my resistance? How many ohms would you say that is?
0.
That would be 0.
Zero, not me.
Okay. All right. So we want to know what our current is.
Uh-oh.
I is equal to E divided by R. And this is a 9-volt battery divided by 0 ohms. What is 9 divided by 0?
9. 0.
Who said 9? It's definitely not 9. What's 9 divided by 0?
0.
It's not 0.
It's like infinity or close to it. Or-
It's as much
Undefined,
current
but
as that
goes to
battery
infinity.
can possibly provide. It's as much current as that battery can possibly provide. Now, remembering, of course, that that's not really a short circuit. That's a poor little diode sitting there. It's going to have this massive amount of current flowing through it, right? So what's going to happen to the diode? It's going to work for a very, very short period of time.
Self-destruct.
Yep. So what you're going to do is you're going to throw a resistor in series with it to actually give the circuit a little bit of resistance. Because once that diode turns on, it becomes a short circuit. So the resistor is there to provide a stable bias current and protect the diode from committing suicide.
So Scott, in the previous diagram, there was a little, I don't understand how the resistor is getting involved. It looked, there was just a little wire coming to the resistor. And
we just drew it.
is there electricity coming through there in some way?
In other words, like this?
Because the battery's on the other side.
Well,
So
the
see the little dot you made?
the big
And then
battery's on the other side.
resistor?
Yeah, this is the input
Okay,
for the circuit.
okay. All right, so, all right. So there is electricity flowing
yeah.
through there.
That's your input for the whole thing.
Okay.
That's
got
what
it.
actually
Okay,
drives the
okay.
whole. That's what actually drives the whole circuit. So this circuit right here is what we're concerned about.
Right.
So this basically becomes a battery, plus and minus, like that. And then ground is ground, so those are connected together. So there's our battery right there. And the resistor is now protecting the diode, which is basically now protecting the transistor.
So what we're saying in the diagram is that on the way to charging up the other battery, the light is going on.
Yep. By virtue of the other, basically because the transistor is essentially two halves. It's split into two pieces. There's the base to emitter junction, and there's the collector to emitter junction. It's really two pieces. If the base to emitter junction becomes active, the collector to emitter junction becomes really, really open. One way to look at what a transistor does is if you have a water pipe with a control valve right here, and by screwing this control valve in and out, that determines how open the pipe is. If you screw the valve all the way in, the pipe is completely closed and you get nothing going through. If you pull the control valve all the way out, the pipe becomes completely open and you get a massive flow. If you do it halfway, if you were to insert it halfway, it would be somewhat restricted and you get half flow.
Okay.
That's essentially how a transistor works. If you think of it with an analogy.
So if there was a setup like this, the purpose of this is to charge up the battery on the right, and the lamp shows you when current is going to that battery
No.
to charge it up.
No. This over here is a completely separate circuit. Whoops. This over here on the right is a completely separate circuit, which is being controlled by the circuit on the left. So what's happening is that essentially the transistor is operating as a go, no-go switch for this path right here. If it allows that circuit to operate, you basically just have a current that flows like this that uses the battery to run the light.
Oh, I see. Okay, it's going the other way. Okay, okay.
Yep.
Okay.
Okay, the next one we're going to do is something that looks like this. Here we go. Okay. All right. This brings in something very important, and we really have to cover it. Okay. So what we're going to look at is, I know I'm redrawing the entire thing, but sometimes it's important to do that. Okay. And finally, whoop, there's a couple of extra new things thrown in here. Okay, so this is our input and this is our output. Okay. This right here is AC voltage. This right here is a fuse. Why do we add a fuse?
To protect the rest of it.
In case something goes wrong.
In case something goes wrong and we end up with too much current. A fuse is a current limiting device. How about this right here?
It's a switch.
On-off switch. To turn something on and off. Excellent. Okay. How about this thing right here? That is a transformer, and that is actually something that we are now going to spend a little bit of time on. Because a transformer, even though it's only very, very briefly discussed on this exam, it's really important to know. Okay, the first thing we're going to ask is, what is that?
Inductor.
That is an inductor, okay. And what does an inductor do as far as energy? It stores what kind of energy?
Magnetic.
Magnetic energy. Stores energy in a magnetic field. Okay, so if we put AC through it, remember we said that inductors kind of look like an open circuit for AC? Well, it's not completely open. It's actually frequency dependent. So what we do is we run AC into our inductor, and what we get is an oscillating magnetic field that goes back and forth, and it fights back a little bit, so it limits the amount of current that flows, but that's okay. So what you end up with is a magnetic field coming out of the inductor that goes like this, but then sometimes the other half of the cycle, it reverses. So we get an oscillating magnetic field coming out of the inductor. Okay, so now what we do with this inductor is we take the coil, because it's just a coil of wire, and we wrap it around iron. Now, iron is a ferromagnetic material, and what it does is it tends to concentrate magnetic fields within itself. So magnetic fields can exist okay in air, but if it sees a material like iron that can be magnetized, oh, yeah, that's definitely better. So what we do is we wrap our coil around iron. Okay, the other trick of this is what happens if you have a magnetic field in space and you stick a wire in it. If a current generates a magnetic field, what does a magnetic field make?
Current.
A current. Okay. So what we've now done is we've taken this iron core right here, and we have constrained our magnetic field inside the iron core, because iron's much better at holding magnetic fields than air. And now we've taken another coil of wire and wrapped it around the other side of the core. So what we've done is basically contained our magnetic field inside the core, and then run that magnetic field on purpose through another set of windings. And that, depending on the number of turns of wire in that particular coil, N1 and N2, that determines the voltages. So let's say that we have, in this particular case, 100 turns of wire on this coil and 10 turns of wire on this core. And this is 120 volts AC. We will get 12 volts AC on the other side. That would be known as a step-down transformer. If we were to change that ratio of turns and make this 1,000 turns, we would actually get 1,200 volts AC on that side, just by changing the ratio of the number of turns of wire. around that core. So, can you think of an application for either one of those?
Battery?
What part of a battery?
I don't know the internal mechanisms of a
I'll give you a
battery.
hint. There's one right here.
Rechargeable battery.
Yeah, but I'm holding one up right here.
A trans
Power supply.
power supply.
All right, because a power supply, you don't need to run 120 volts DC into your computer. Your computer runs on about 19.5 volts DC. Well, that means you don't need all that voltage, so what you would have is a step-down transformer. Where else would you find a step-down transformer? And I'll give you a hint. The voltage that it's stepping down from is 12,700 volts.
Transmission lines.
Transmission line. You look out on your power pole the next time you go outside. Look at the transformer that's feeding your house. You'll have a 12,700 volt transmission line, or sometimes higher, feeding it, and you have a nice clean 120 volts AC coming out of the other side. That would be a step down transformer. When would you ever use a step up transformer?
On the other end.
On the other end, let's say you're at the power station and you're generating voltage at 3,000 volts. And your high voltage transmission lines, which are what you, for instance, drive under when you're on the interstate, those are operating at 345,000 volts, maybe 600,000 volts AC. Some of them are operating at 800,000 volts AC. Some of them are operating at millions of volts DC, but we're not going to go into that because that's a much more complicated circuit. But so transformers, if you see a substation, those transformers, you'll see 3 transformers in parallel. They're operating with on different phases of the power. Those are basically all responsible for transforming up and transforming down the voltages, so that you can transform them up for long distance transmission, and you can transform them down for being used by your local person.
So Scott,
Yep.
so here's my computer adapter that you're
Uh-huh.
talking about. How come you always see them on computers, but you hardly ever see them on other appliances? Are they just embedded inside the appliances, like your
can't-
toaster and your
Well, no,
coffee
because
maker?
that depends. A coffee maker. Okay, so think about it. What's Ohm's law for power? Power is equal to what? Power is equal to I times E. Power is equal to current times voltage. Okay, if you want the same amount of power, what are the 2 things you can alter?
Current or voltage?
Current and voltage. Okay, good. Now, let's say that you want to transfer a certain amount of power. All right, what's the other part of Ohm's law? E is equal to what?
IR.
I times R. Okay, that's good. All right, so now let us say that we have gone through and we say we want 1,000 watts. Right? This is actually great that we're doing this. Let's say that we want 1,000 amps at 1 volt. Can we do that? Sure. Right? The math says sure, why not? Okay, or we could do 1,000 volts at 1 amp. Okay, here we go. Does the resistor care? Nope, not really. Now, what does matter is that every piece of wire has resistance built into it because of what it is. Right? Wire is not perfect. It has length, and it also has a cross-sectional area. Those things figure into its resistance. So, how do you make wire have a low resistance? You make it short and you make it fat, right? The more cross-sectional area it has, the more current it can handle, and the shorter it is, the less resistance it has. If you were to take this wire and you stretch it out really thin and make it really long, the resistance goes up, okay? So now we're going to look at this one, E equals I times R. The resistance of this wire is very low. The resistance of this wire is very high. Well, if I have a fixed current going into it, which one is going to have more of a voltage drop across it if I measure it? If I have the same amount of current flowing into it and going through it, this is going to be low voltage drop. This is going to be a very high voltage drop. Okay? Well, that being said, we go back to our power is equal to I times E. This is going to be low power loss. This is going to be high power loss. If I am the power company, which one do I like? Low power loss or high power loss?
Low.
Low power loss, exactly, because that means I can service my customers. So, you obviously like to operate at low current. You also like to operate at, if you want, well, if you're going to provide power lines, would you rather provide the thin power lines or the fat power lines? On a cost basis.
Yeah.
You would definitely go for the thin ones,
Thin ones, yeah.
right? Because thin ones don't cost nearly as much, and you don't have to have as big of a structure to support them. So basically, in order to do that, what you would do is you would go with thin power lines and very, very high voltages, because that keeps your currents down. So that is why you have a choice. You can either do this or this. That is much more popular. And that's why if you get a toaster, for instance, or let's say you have a an air fryer like we love at our house, right? That air fryer has heating elements. The heating elements operate at high voltage, but it also has a touch panel, right? Which is basically a computer. So internally there is a power supply that generates a control voltage to run the touch panel, a very low DC voltage, but there's still the external voltage coming in that's then used to turn on the heaters. So there's a power supply in there, you just don't see it. Okay, so let's see. We started to get into our transformer. Our transformer did what we wanted it to. And what I'm actually going to do is I'm going to draw this again, where we have our this, and we have our fuse and our switch. And I'm sorry, this is taking a little while, but we'll get to it. That's our fuse. Here's our switch. Here's our transformer, changing our voltage from 120 AC to, let's say, 12 AC. And then we have this feeding into a diode, and this then being filtered right here, and that, and that. Okay. Okay, here we go. So we now have switched our voltage from 120 AC to 12 volts AC. So what we're going to draw is a little bit of a diagram. What is that right there?
AC.
AC. Okay. Now, we just said that when we get to a diode, when the voltage goes on the positive side, it works, but when it goes on the negative side, it doesn't. So what does the voltage look like coming out of the diode? It looks like this. It looks like a train of pulses. And they're always positive. This is direct current, which is DC. Now, we also said that a capacitor, when it charges up, unless something happens to it, that charge remains there. right? Well, so what happens in this case is that that capacitor charges up until the voltage goes away, in which case the voltage then begins to, the charges tend to flow back out of the capacitor. So the capacitor then acts as a filter, and instead of looking that ugly, maybe it looks like this. So it's kind of like a wobbly DC now. So that doesn't look quite so bad. That's a little bit of filtering. Okay, so now we have this thing right here. This is an LED. It turns on when there's voltage over here. And now, since there's always voltage over here, the LED is on all the time. All right, element 9 right here. They label it as element 9. That's a variable resistor or a potentiometer. And finally, the purpose of the resistor is to limit the output current of the power supply. Again, by changing that value, that determines, even if there's a short circuit on the output, there's a little bit of resistance that we've thrown in to limit it. And then finally, we have this special looking thing all the way on the right-hand side. And this, does that look like a diode, everyone?
Yes.
Okay. It's a special diode. Remember we said that every diode has a tendency to do this and work in the forward direction? This is a special diode. This is a special diode because it's actually designed to work in the reverse direction, which is why it has that little thing on it. But it doesn't just work in that reverse direction. This is actually a Zener diode, and it's a voltage regulating diode. It says, okay, well, I'm going to let you turn on in this direction, but I'm going to put a reference voltage on your output. And no matter what happens, I'm never going to go higher than, let's say, 9 volts. If it's a 9-volt Zener, you basically buy the component based on the voltage that you want it to work at. So essentially what happens is that when it comes on, when there's voltage above it, what happens is that it takes everything above that voltage and it does this with it. So let's say this is the Ripley voltage coming in. It says, okay, I'll work, but your voltage isn't going to go any higher than that. So anything above, this is all wiped out. And what do you have? You have nice, clean DC voltage. This is known as a DC power supply. And in particular, this is because your voltage that comes in is being converted half of the time, not all of the time. This is known as a half wave rectifying power supply. Now, what's not so efficient about it? What happened to all this down here? Where did that go?
Heat?
Yeah, we just turned it off.
Oh.
We said, we're not going to use it. So a half-wave rectifying power supply is not all that efficient, but it's very, very simple. So we could actually build a power supply that instead of being half-wave rectifying was full-wave rectifying, except that instead of a single diode, we would basically have something that looks like this. So here's our input, and here's our output, right there. And when this went positive, our path would go like this, and then out from here, and then, so our diode looks like that, and then another diode looks like that, and then it goes back to where it started. When the voltage switched, our plus is now over here, and so our path goes like through here, and then it comes up through here, and then out and around to here, and it goes like that. And back out. Okay, how many diodes do you see?
Or
Yep, so full wave rectification requires 4 diodes. But the nice thing about it is that it's always operating. So that, let's say that you have a signal that looks like this coming in, the output will look like this. It rectifies or fixes the entire wave. It uses the entire waveform. So it's more efficient. And that's known as full wave rectification. Okay, finally, and then we're going to take a break after this. What we're going to draw is this circuit. Here we go. Okay. Okay. What is component number 2, everybody?
Capacitor?
A capacitor. What does the arrow across it mean?
Variable?
It means it's variable. That's right. Okay. How about number 3?
That's a
Variable inductor?
That's a variable inductor. Okay. And how about number 4? Number 4 is an antenna. Okay, so what we have here is a device that has 2 variable capacitors and 1 variable inductor in the form of a letter T. This is actually called a T network. Now, I could also do it where it looked like this. Any idea what letter that what that would be called? Instead of a T network? Think Greek letters.
pi.
That would be a pi network. That's known as a pi network. So the reason that we do this stuff is because, now, think back to a capacitor. Capacitor has this thing called impedance, and so does an inductor. All right? Capacitors have negative impedance. Inductors have positive impedance. So what we have here is an impedance over here coming in off this antenna. The antenna has an impedance. And we also have a transmitter over here that has an impedance. Or it's actually our transceiver. It's a transmitter and receiver. So what this allows us to do is it allows us to say, okay, here's the impedance of our antenna over here. And then we have a negative impedance right there. What happens if we have an impedance in series with another impedance? Impedances are just like resistances. They add together. Well, so now we have these guys in series with each other. Well, what happens if we then add another impedance, but effectively it's in parallel? So we then have a different formula. So like we had Z1 plus Z2. Now for this whole thing we have Z1 plus Z2 times Z3 over Z1 plus Z2 plus Z3. And then we have all of that in series with that, number 2. So this actually that's a pretty complicated math problem, right? So what we're going to do is ignore all that math. We're going to get rid of all of it. And we're going to distill it to what's really important here. You notice the fact that each of those is a variable value, right? You see the little arrows across them? Okay, the fact that they're variable means that they can be tuned, because the impedance of a capacitor is -1 over 2 pi fc, and for an inductor it's 2 pi fl. So notice we have our frequency that shows up in both, and we also have an inductance which is now variable, and a capacitance which can be varied twice, 2 different ones. So what we can then do is we can then use this to create something called a T-type antenna tuner. And that looks like this. And notice what we have, everybody. We have two knobs that say antenna and transmitter. And what does that little clicker say? That's that rotary knob there. It says inductance, and it has different settings. What this allows us to do is it allows us to match the impedance of an antenna to the impedance of our transmitter.
That's got the question.
Yep.
The impedance is, if I remember correctly, it's basically the resistance,
Nope.
the effective resistance.
Nope. Impedance is what happens to something. Resistance is for DC. Impedance is for AC.
Okay.
Impedance is something's ability to resist the flow of AC current.
Okay,
Okay.
so the difference is impedance is works or impede it restricts AC, and
Correct.
resistance works on DC.
Correct. And
So
since
it's kind of what we created here is a potentiometer for AC currents.
no, what we've created is a variable, essentially a variable changer for, like, for instance, if I were to say, okay, here's my antenna, and my antenna has an impedance of 50 ohms. And I come down here, my cable has an impedance of, let's say, 75 ohms. I would have a mismatch, and I have some, looking out into the cable, I would have an impedance of question mark. Most transmitters have a characteristic impedance of 50 ohms. They want to see a 50 ohm antenna. They want to see 50 ohm cable. So we have this device, which is a matching device, which through the magic of capacitors and inductors and having them be variable allows us to change and add or subtract impedance from the outside world so that that question mark becomes something that is now predictable. It's essentially a tuned circuit that allows us to modify what the impedance looks like.
Okay,
And that's
so
known as
in this
impedance
case,
matching.
is the impedance that's coming into the thing that fixes, was that 50 plus 7, was it 75?
It is not. Now that's another important thing. That's a very good distinction, because if I have an impedance, let's say this is 50 ohms, and we're actually going to do feed lines next. A feed line has something called a characteristic impedance. So this device right here, that has what would be called a lumped impedance, which has basically, it's just 50 ohms impedance. That would be its value. A characteristic impedance, if this was a 50 ohm cable that had a characteristic of 50 ohms, the impedance looking into that whole system would be 50 ohms. Because a characteristic impedance is not a lumped impedance, it's kind of like it's kind of like looking through a tunnel. And if the tunnel matches the device at the end, then it's like the tunnel's not even there. It's a little hard to fathom, but the reason that it is that there's really it's not a transmission line or a piece of cable is not designed to use any power. It's just designed to be a conduit for power. So because of that, it's really just saying Okay, well, if I have a 50 ohm load over here and a 50 ohm source, and they're both 50 ohms, then this thing in between is designed to couple the two together. That's the function of a transmission line. It's designed to couple a source and a load together. And it has a characteristic impedance that's based on its, believe it or not, geometry, how it's built, what its components are.
So let's say it's our characteristic impedance of the feed line is 75 ohms.
Yep, which is
Well,
cable
now what
TV
happens?
cable. Well, what happens is that depending on the length of that feed line, that will actually alter the impedance that's viewed at the source.
Right. And
And
there's
if it's
some
and
way to calculate that, but
that is on the extra class exam.
okay.
And that
All right.
that is something called a Smith chart. If you want to do additional stuff, there's something called a Smith chart that's used for doing things like that. Because basically the transmission line will act as an impedance matching transformer at that point. And a Smith chart is used to figure out what that does. And if you've ever seen one, it kind of looks like this. It has two different sets of curves. There's a resistance axis and a reactance axis. And that's on the extra class exam. Very, very useful. They teach them in college as well for just that reason. Okay, we're going to do one more page and then take a break. What's a relay? A relay is an electrically controlled switch, essentially using a magnetic switch to close a pair of contacts. A device that displays an electrical quantity and a numeric value is known as a meter, such as a voltmeter or an ohm meter or an ammeter. A device that contains several semiconductors and other components in one package is called an integrated circuit. We saw this a little while ago. We're on page 23, by the way. Type of circuit that controls the amount of voltage from a power supply. We had a Zener diode. That's a regulating device, a voltage regulator. If you have a car and you have something that goes out in your charging circuit, you can lose the voltage regulator that's responsible for charging the battery. You've already heard the term. Which of the following is a common use of shielded wire? Shielded wire is great because two wires that are parallel to each other tend to couple together because of magnetic fields. By shielding the wire, we basically create a little environment by which all of the energy is contained inside an area. So if you shield two wires, you put them next to each other, they won't couple to each other. Okay, so when we come back after a 5-minute break, we're going to skip over all the propagation stuff because we just did it. And then we already did antennas, and we're going to segue into feed lines. And feed lines are on page 36. All right, 5-minute break, everyone. Think of questions.
All right.
All right, everybody, who's got questions?
I have a question about the test. So, what do you need to do to pass again? How many do you need to get?
73%.
73%.
26 out of 35.
Okay. I've been
Basic-
taking the practice tests, and I like started out and I was getting like 20-30%, but I've been getting like in the 60%, 65% right now.
Keep going. There you go.
I'm like getting closer.
Good. That's what's supposed to happen. So, Knight,
Yes, sir.
how's the season going?
I mean, we won yesterday, so we're 7-12 now.
Okay.
So like, we had a 5-game losing streak, and then in the middle of that 5-game losing streak, our coach got tossed, and so that was kind of like a little bit of a rough stretch. But I feel like things are starting to feel a little bit better. I don't know.
Well, when you say the coach got tossed, like ejected from a game or fired?
Yeah. Like, well, he got ejected from the game.
Okay,
And
well,
it was like something that stemmed from like a series prior. So they got swept in Wenatchee, and the umpires were apparently like terrible. And then the umpire called our coach numerous slurs. And then
really?
yeah. And
Wow.
our coach was like, so like, when are you gonna start calling like the right, or like when are you gonna start watching the game or something like that? And then the guy like cussed at him for 2 minutes and then threw him out.
Really?
Yeah. And that was like weird too, because like I had never like broadcast a coach being ejected. And it was great too, because I literally had talked to him that game, or like
Yeah.
right before the game, said, hey, like, you get tossed, you come to the booth, I come to the field, you know, like, let's do it. And he was like, yeah, let's do it. And he like told me all, I was like, well, have you ever been ejected from a game? And he was like, well, I've been ejected from 3 games. And he like told me all the times he had ever been ejected. And it worked out, because when he got ejected, I got to tell all those stories. So I was like unintentional prep. I like jinxed him getting ejected in one game, but I don't know. It was wild, but I think things are like starting to go in the right direction. I feel
So,
like
did you say he was ejected or given the heave ho, or?
well, he was ejected, and then he was suspended for 4 games.
Oh, he
and
was
then
suspended?
They suspended him for 4 games because he, instead of going to the locker room, he like went and sat in the bullpen with the players.
Oh yeah, you're not supposed to do that.
So he wasn't allowed to do that, and so he got suspended 4 games. They appealed the suspension, and it got reduced down to 1.
Okay. Well,
So he only ended up missing 1 game.
is he going to spend it in the booth? Did he spend it in the booth with you?
No, he spent it in the locker room. He's not allowed in the booth, but he watched my
okay.
entire broadcast. So
Okay.
that was cool for him, because he had like never listened to me broadcast. Like I had just done like the pregame interviews, and like
Yeah.
he had heard some of the highlights and whatnot. But he like sat down. He was like, "Bro, you're like actually like good at broadcasting." And I was like, "Yeah."
Oh yeah, he's still all surprised. Thanks.
Yesterday, I had like one of our pitchers come in and like do color commentating,
Nice.
which was like really, really fun, because it was just like a non-league game. And so he came on, and we just like cracked jokes the entire time. Like it
You
was
say, I want to replace Joe Buck. I want to replace John Miller, guys.
yeah, I'm not gonna replace them. John Miller can have that job as long as he wants.
Yeah. All right. Other questions?
Yeah, so to go back to the last diagram, you talked about matching the impedance from a
Yep.
from a load to a source to a transceiver kind of thing.
Yep.
And you try and match it like the 50 ohms all the way through. But if you find out if your feed line or whatever is makes it 75 or something, that's when you use that little black box
Yep. It's
that
called
you
an-
showed
Yep.
to match to tune it to match the impedance the rest of the way, right? So that
Yep.
the load and the source. Okay.
And like, okay, let's see. Okay, so we're talking about feed lines and connectors. Okay, so a feed line is a device that is used to connect a source to a load. So basically, the goal is that your source is your transmitter, your load is your antenna. It can actually be a resistor or anything like that, but the source is what's making power, and the load is what's using power. So, okay. So, what's important to note is, like for instance, why is coaxial cable so popular? Well, coaxial cable is popular because coaxial cable looks like this. Everyone has probably seen something like this at some point. And notice you have an outer jacket, then you have a braid, then an inner insulation, and then a center conductor. And no matter what you have, notice that they all are basically built the exact same way. So what's nice about this is that all of the energy that's being carried in the cable exists in between the shield, which is that braided steel or aluminum or copper, and the center conductor. Notice that most of that is inside plastic, depending on the size of the cable that you're looking at. So notice you've got RG58, 59, 62, 6, and 11. If we were to look at this, we would say, okay, how are these cables different? Well, they're obviously different sizes. They probably have slightly different materials that they're made from. Notice some of them have a double shield. Some have like a braid over foil. Some are copper, some are aluminum. Some of them, the geometry is a little different. Well, it turns out that RG58 is 50 ohm cable, and the other four that are there are 75 ohm cable, which basically means that those 75 ohm cables, which are 59, 62, 6, and 11, are simply scaled versions of each other. The geometry is exactly the same. The materials are going to be very much the same. To change it to a different impedance, the physical characteristics of the 58 are going to be a little bit different, let's say from the 59. They're about the same size, but you can see that the geometry is a little bit different, and it's very subtle. And even within, for instance, RG, notice that there's lots of different ones. There's RG59, RG6, RG7, RG11. The most common one that we use is known as RG58. And the reason we use RG58 is because it's 50 ohms. And it's also, for instance, if you get a mobile antenna and you stick it on your roof, you can slam it in your door, and it doesn't, and it still allows the door to seal, and it doesn't destroy the cable. Now, if we were to use, for instance, RG8, we would find that RG8 is considerably thicker. Like I'm going to show you hopefully a picture of RG8. Oh, here we go. So these are different of different variety of cables. If it lets me do that, darn it. All right, I'm having a little trouble here, so give me a second, everyone. Oh, here we go. That's a good picture. Okay, so can everybody see that? Okay, so RG8 on the right-hand side and RG213. Notice that RG213 is a lot thicker. They're both 50 ohm cables. The one next to it, RG174, that's also a 50 ohm cable. Notice that it's a little bit thinner. That's something that you would typically use for a very, very short run. RG 405, notice that looks really big and really solid. That's something that you would typically use for a very, very long run or at very, very high frequency. Because the way that cables work is that the higher you go in frequency, the worse the loss becomes. Let me say that again. The higher the frequency at which you're using it, the worse the loss becomes. In addition, the smaller the cable you use, the worse the loss becomes. So, for instance, I could pick coaxial cable loss. Graph. And notice there are probably many choices to choose from. Let's just pick one. And hope that this is legit. There we go. There's a good graph. Okay, so notice we have different cables. And we have curves for those cables. There we go. And notice for 9913, 9913F, and so on and so forth. So we have power output given power input. And as the frequency goes up, our signal transmission gets worse and worse and worse. Similarly, we also have, let's see, cable loss, coaxial cable loss. Ooh, that's a good one right there. Per 100 feet. Here we go, at different frequencies. That chart that's right in the middle, darn it, wasn't supposed to change. There we go. Notice that, let's pick a particular cable. One of my favorites, RG8X, it's a nice intermediate cable. At 1 megahertz, its loss is 0.5 decibels per 100 feet. At 100 megahertz, it went all the way up to 3.6 decibels. At 700 megahertz, it went all the way up to 11 decibels. At a gigahertz, it's 13.5 decibels. Now, that doesn't necessarily seem like a lot, but what do we know about 13.5 decibels of loss? If we go back to our math from yesterday, 13, we'll assume it's 13. That's 10 plus 3, which is 10 times, and 2 times is 20 times. And since it's loss, we're losing, you know, we're cutting down our transmitted power by 1/20th, which means if we're using 100 watts, we actually get 5 watts out. So what happens to the other 95 watts?
Heat.
Heat.
Lost.
It heats the cable. It just heats the cable up. So if we switched over to, let's say, this RF 9913 at that same frequency, we'd be all the way in the lower right-hand corner at 4.5 decibels, which is about halfway between 3 and 6. So, you know, 3 would be 2 times and 6 would be 4 times. So let's say we lose, you know, it's about 3 times. So we lose a third of our power. You know, we cut it down to a third. So for 100 watts, we're still getting 35 watts out. That's a lot more acceptable than, you know, knocking it all the way down to 5 watts. And that's why we have different cables available to us. Now, that 9913 is a lot more expensive and it's a lot bigger. But the question is, are you going to be operating at 1 gigahertz? The answer is, I don't know. It depends on what the system is that you're putting in. If you're putting in a cell phone site, you know, where you're operating at 1 or 2 gigahertz, then the answer is yes. If you're operating on the 400 megahertz band, a 440 megahertz or 70 centimeter band, maybe it doesn't matter so much. If you're operating on HF, let's say the 10 megahertz or 30 meter band, and your loss is either 1 dB versus 0.4 dB, who cares? Doesn't really matter. And that's why it's important to understand how all this comes into play. So why is coaxial cable the most common feed line used for amateur radio antenna systems? And that's because it's really easy to handle. You can bury it. You can hang it outside. You can waterproof it. Now, it's really important to waterproof it because water is the one thing that will destroy cable. Again, impedance, the measure of the opposition of AC current flow in a circuit, measured in ohms. Most coaxial cables used in amateur radio are 50 ohms in characteristic impedance. The reason being that most transmitters that are built for ham radio are 50 ohms in characteristic impedance. A lot of antennas are 50 ohms in impedance. It turns out that 50 ohms is kind of a sweet spot where you can actually optimize your power transfer. So 50 ohms is a really good impedance to have standardized on. RG8 and RG58 are two very popular cables. There's also something called RG8X, which is a little bit bigger. So in general, what happens as the frequency of a signal going through cable increases, and that would mean the loss goes up, as we showed on the graph. Similarly, if you have a smaller and smaller cable, your loss increases across the board. The main difference between RG8 and RG58, so I'm going to draw RG8. And I'm going to draw RG58.
What did you just say if it was smaller and smaller?
Here we go. This is RG8, and this is RG58. And I can also draw the RG174. These are all 50 ohm cables, drawn roughly to scale. Which one is going to work best for transmitting power at any frequency?
RG8.
RG8, because it's physically the biggest. All right, which one's going to weigh the most and be the most expensive?
The middle.
RG8.
Yeah, RG8, right? RG174 is going to be very lossy, and as your frequency goes up, it's going to be basically unusable. In addition to that, which one is going to be able to handle the most power?
RG8.
RG8, that's right. So for high power applications, you would typically use RG8. If you're using something with a really high frequency, then RG8 might not even be good enough to use, and you might need something even more expensive and bigger.
If it was high frequency,
High frequency, I typically use RG58 because the losses are fairly minimal and it's easy to work with. If I have a really short run, let's say I have a 6-inch run of cable and I need to get from place to place, I could use RG174 because it's measured, remember, in dB is in loss, losses dB per 100 feet. So what if my cable's only 6 inches long? Yeah, I can make that up.
Yeah.
So that's why if you're dealing with, even with very, very high frequency circuits, let's say you're building a satellite and you have two boards that are 3 inches apart, you can use really tiny cable just to move the signal from place to place, and it's not a big deal. Okay, which of the following types of feed line has the lowest loss at VHF and UHF? That would be whatever's bigger than RG8. And that would be something called air-insulated hardline. Now, that's because it's, let's say, this big. And instead of using a plastic for an insulator in here, it actually uses air in between the shield and the center conductor. That air, instead of being air, because air has moisture in it, and what does moisture cause? Moisture causes corrosion. It causes corrosion. Very often, if you're doing something like that and you have air, then what you would do is you would evacuate the air and use nitrogen instead. That also means that it has to be pressure sealed, which means it has to be really well sealed. It also means you have to have it hooked up to a nitrogen tank. It also means that somebody has to maintain the heck out of it. Most people do not go to that end unless you're putting in a commercial installation. The most common cause for failure of coaxial cable is moisture. If you get moisture inside your cable, you will get corrosion, and then it doesn't work anymore. Why should your jacket of your cable be resistant to ultraviolet? Because if it's not resistant to ultraviolet and it's out in the sun, it'll crack, and then what gets in through the crack?
Moisture.
Moisture. There you go. So it really all comes down to the same thing. A disadvantage of air core cables. when compared to foam or solid dielectric types. Dielectric is basically like a plastic or any material that doesn't conduct, like air. Again, if you're filling it with air, that means you need to use special techniques to prevent water absorption. You fill it with dry nitrogen. Following type, which of the following is true of a PL259? Okay, you're going to see lots of these on the air when you're operating. PL259. This is a PL259. Right here. That's a PL259 connector. Those are the industry standard for PL259s. Right? These are the industry standard for high frequency radio. And most of the time VHF as well. Well, the interesting thing about PL259s is that these are often called UHF connectors. Notice this says UHF male to UHF female, or UHF male to male. UHF chassis mount. That does not mean UHF. Don't be confused by this. UHF in this case means universal high frequency. And notice this says N male to UHF female. Well, this is an N on the left-hand side of it. Can everybody see that? It has like a double shield. On the other side is just an SO239. Very, very bad connector for UHF, even though sometimes they're called UHF. This is technically, again, it stands for universal high frequency, not ultra high frequency. So, these are very commonly used at high frequencies. If you're going to higher frequencies, you would typically use something that looks like an N connector. And an N connector looks like that. Notice it's got double shielding. There's an N connector. There's an N connector. There's an N connector. And in fact, there's even a Wikipedia entry for N connector. Notice it's got a rubber gasket, so it's actually waterproof. And that's actually really helpful. There's a close-up view of N connectors. N connectors are great to even 400 megahertz, even up to the gigahertz range. Microwaves. N connectors are great. There's also something called an SMA connector. An SMA connector is a little threaded connector, very, very small, which is actually used on most handheld radios these days that have a removable antenna. And they look just like that. Those are SMA connectors. One is a male, one is a female, depending on whether it has a pin sticking out or not. Here's the top of my radio. That is an SMA female. Here's the antenna. That's an SMA male connector. The advantage of SMA is that SMA connectors are good into the gigahertz range as well. And they're fairly inexpensive and fairly rugged.
Scott, what would be the connection that's used in cable, like at homes?
That's an F connector, it's called.
An F?
Yep. So yeah, we don't use those. They tend to fail after a while, but they're fairly inexpensive. Why should coax connectors be exposed to the weather, be shielded against water intrusion? Because, again, if you get water through your connector, the water will get into the cable, and what happens?
Erosion, and it won't work.
Yep, you'll end up with an increase in feed line loss. Or, in other words, your cable is now crap. What can cause erratic changes in SWR readings? SWR is standing wave ratio. If you have a loose connector somewhere, that can cause erratic readings. And in fact, on the very next page, we're doing standing wave ratio and antenna measurements. So we are on now page 39. And what I'm going to do is grab the whiteboard again, and I'm going to draw this jump rope, which is connected to a doorknob. Has anyone ever done this? Just for fun?
Yeah.
Okay, so what happens if you stand over here and you whip the jump rope, what will happen to the jump rope?
It's tangled around the doorknob.
Yeah, well, what
Oscillate?
you'll see is you'll see a
Okay, the
wave
wave.
on it, and the wave will travel to the doorknob. All right, what happens when it hits the doorknob if the door is closed?
Bounce back.
It bounces back. And in fact, it'll bounce back underneath. Because that energy has to be neither created nor destroyed. The energy has to come out somewhere, and there you go. The energy has to be reflected at this point. This right here would be considered a mismatch. Because, ideally, let's say you, instead of a doorknob, managed to find a taut jump rope that went on forever. Let's say you could find a taut jump rope that went on forever. And you whipped it one time, and you found that you created this wave, and where would the wave end up? Where would the wave go?
Just keep going.
It'd just keep going, because that jump rope exists forever. That would be called a perfect match, because the energy that you put in ended up somewhere, but you never saw it again, which means it must have gone out into the world. That is the difference between a mismatch and a match in impedance. So a properly matched system, you'll put power out into the world and you'll never see it again. Let's say that you have your transmitter down here, and you go through your feed line, and your feed line is 50 ohms, and this is 50 ohms, and you have an open circuit, which has an impedance of basically infinity. There's no antenna hooked up. Your signal goes up the feed line. It gets to this point where it has to decide something. Well, what happens to the energy? It can't go out. What's going to happen to it?
Heat?
Nope. It can't go out. What's going to happen?
Doesn't come back.
It's going to come right back. Okay, so this is your forward, and this is your reflected. So what's going to happen instead if this is a short circuit? What's going to happen to your energy?
All of it goes back.
All of it's going to come back, right? The polarity is going to change, but all of it's going to come back, which basically means that all the energy you put out into the world, 100% of it came back. This would be known as an infinite SWR. You have as much energy coming back as you have going out. Standing wave ratio, or SWR, is a measurement of how much energy is going out versus the wave that's coming back. So basically what you end up doing is you have 2 watt meters. You can measure the amount of forward traveling RF energy in watts, and you can measure the amount of reflected RF energy in watts. And you use diodes to do this. You use diodes to do this, and what you end up doing with this is you can either calculate it yourself, or we're going to do this, MFJ 949E. We're going to show this picture right here. And notice what we have on this screen eventually. What do we have there a picture of? Notice it says forward and reflected watts. We have two different meters. We have one for forward and one for reflected. We want our forward power to be forward, and we want no reflected power. Where the two needles that we have intersect tells us what our standing wave ratio is and how good our match is. So we could actually calculate this mathematically, or we could get an antenna tuner that has a dual needle watt meter that will tell us what it is. Some radios actually have an SWR calculator built into them. They will tell you on a graph what your standing wave ratio is.
So Scott,
Yep.
in the book, it says that it should be 1.
Yep.
Or as close to 1 as possible, but on the picture that you showed, it didn't look like there was a 1.
1 is with it lying completely flat on the ground. 1 to 1 is all the way on the right-hand side, lying totally flat.
Okay.
Basically, if you have no reflected power, notice there's a 0 over there. That means you have a good match. That's what you aim for.
Okay.
So a perfect SWR is 1 to 1. So SWR is a measure of how well a load is matched to a transmission line. Okay, a perfect SWR is 1 to 1. An SWR of 4 to 1 is a pretty serious impedance mismatch. And
What did you say was a serious?
4 to 1. If you have
Okay.
4 to 1, that's a pretty big problem.
Okay.
And the reason that it's a big problem is, let's say you have your signal going up and your signal coming down. Okay, and here's your transmitter. What is inside your transmitter making that signal? What is the physical device that's making that signal to send out into the world?
Diode.
Transistors.
Transistors. Right? You have transistors. Okay, so let's say that your transistor is designed to operate at a maximum of like 36 volts. Right? For whatever reason, that's the maximum operating voltage of a transistor. Okay, so you have power going up to the antenna, and it actually has a voltage, right? It looks like this. But then you also have power coming down. Well, and maybe it's a different phase and it's a different amplitude, but it comes back down. What happens when they get down there? What happens when it gets back to the bottom? They add together. They add together. Well, if they happen to be lined up, and this is already, let's say, 32 volts, which is legal. You already said it's within the spec, and this is 12 volts. What happens if they add together?
48.
Well, you got
44.
32 and 12 is 44. And what did we say the maximum transistor voltage was?
36.
36. Kapow! What did you just do? You just blew up your amplifier circuit. So that's why it's important to have, that's one of the reasons it's very important to have a low SWR. That is one of the main reasons that we do something like this and use an antenna tuner on HF radios and antennas. Because they are there, number one, to get all your power at least going up to into the air, and number two, to protect your transistors in your amplifier from being destroyed. What happens to power loss in a feed line? It disappears as heat. Why is it important to have low SWR when using coaxial cable feed line? Because loss turns into heat. Heat does not make a transmitted signal. If you're going to use a standing wave ratio meter, you want it as close to the transmitter as you can put it. And now, we are all lucky in a lot of ways. If we are dealing with something other than a handheld radio, this will probably not happen, where you blow up your transistors. A handheld radio, you'll still blow up your transistors and destroy your HT. For most larger radios, they do something called fold back. The reason they fold back is because they have standing wave ratio sensors built in. And they know when the ratio is getting high and you're having a lot of power coming back. And so what'll happen is if they sense that the SWR is like 3 to 1 or 4 to 1, they will actually intentionally say, okay, I know when that happens, I'm going to get close to my voltage threshold on my transistor. So what I'm going to do is I'm going to limit the amount of the transmitted signal So I know that the amount of the reflected signal will also be small, and the whole sum will be safe for my transistors. And that's known as fold back. And it's to reduce the likelihood of damage to the transmitter circuit. Okay, an antenna analyzer. So what we're also talking about is something called an antenna analyzer. Now, if I were to take a frequency response picture of my antenna, and let's say I had from 0 up to infinity megahertz, I would see that my SWR of my antenna might look something like this. There might be a couple of times that it dips and is actually really useful. Well, let's say that I've picked it so that this is the one that I want. The question is, how do I legally sweep all those different frequencies when my legally operated transmitting ranges are here and here and here, and nowhere in between? The tricky thing happens if, let's say that instead of doing that, I find that my antenna is behaving like this. And nowhere where I can legally check by transmitting into the antenna do I see that it behaves at all. Right? Because I can only transmit in the blue ranges. What do? What I do is I use this thing called an antenna analyzer. And what an antenna analyzer does is that we're going to cover this is a part 15 device. Amateur radio is covered by this thing called part 97 in the FCC rules. That determines where we can legally transmit on the air. Part 15, if you look at everything else in your house, your cell phone, your power supply, a battery pack, everything will say this is a Part 15 device. A Part 15 device is an unlicensed, very low power transmitter of energy that also has to accept all forms of interference from everything else in the world. So, because it's so low power, a Part 15 device can actually transmit everywhere if the power is low enough and give me a complete test of everything that I'm doing. What's nice about that is that I can see, oh, okay, well, I've got this antenna dip right here and another one here. I wonder how I can actually modify my antenna to make that work. So an antenna analyzer is very good for getting measurements for your antenna over an entire frequency range, even those that you can't legally transmit it. Let's see. Is this in multiples of a fundamental frequency acting like harmonics and mechanical sound? It kind of is, yes. You may notice that if I still have it up, I don't, but I will. Here, we're going to put this up on the screen. Okay, so we're going to look at the old school bands. What's this first frequency that I'm highlighting here? 1.8 megahertz. What would 2 times that be?
3.6.
3.6. Look at that. 3.6 is in a ham band. It's in the 80 meter band. What would 2 times that be?
162.
7.2? Well,
1.2.
guess what? That's in the middle of the 40 meter band. Okay, what's 2 times that? 14.4. Okay, so that's a little bit off of the 20 meter band. So let's go to 14.2 for the next one. Well, 2 times that. Actually, we'll go back to the 7. What's 3 times that? That would be up here in the 15 meter band. And 4 times that would be right here in the 10 meter band. And yes, there is a reason for that, and that is because when people used to build their own transmitters, it was a lot safer for people to generate harmonic frequencies in ham bands than it was to generate harmonic frequencies in other services, let's say air traffic control. Right. One you could remedy with little issues, you know, and the other one, if it happened, it might cause a plane to lose contact with the ground.
You lost me.
Hmm?
You lost me.
I lost which one?
Yeah, through that deal right there.
Okay, well let's do it like this. Let's start at 2 megahertz. What's 2 times 2?
4.
Okay, that's the upper edge of a ham band. What's 2
Okay.
times that? Let's say 3.5. What's 2 times 3.5?
7.
7.
Okay, that's the 40 meter band. What's 2 times that?
14.
Okay, that is 2 times, that's the 20 meter band. And we'll go back to the 7. What's 3 times that?
21.
21. That's the 15 meter band. What's 4 times 7?
28.
That'd be
28.
28. That's the 10 meter band. The bands that were initially come up with for ham radio were harmonically related because it's a lot easier to generate harmonics of frequencies accidentally.
See, that's where you lost me. Harmonics of frequency
Uh-huh.
means what?
Uh,
That
Multiples.
the frequency is
anyone
harmonious?
play music?
No. Play it, yeah.
Yes.
Okay.
Listen.
I'm learning how to play guitar.
Okay. So an A is 440 hertz. 1 octave up, an A is 880 hertz. The next octave up, an A is 1760 hertz. They're multiples of each. Basically, those are harmonics.
Okay.
A harmonic is an integer multiple of a frequency.
So were people, when you say it was hams, it was easier to generate a harmonic?
Well, not on purpose.
Why? Why was it easier?
Not on purpose,
Was
but
that accidentally?
usually yes.
Okay.
If you're building your own equipment, it's a lot easier for a transmitter to generate a harmonic than anything else.
Would you give an example of an error that will generate an harmonic accidentally?
I mean, basically, if you're building an amplifier, sometimes you'll have it's much easier to generate a harmonic than it is to generate some random frequency. I mean, just harmonics are something that are typically what can come out of a transmitter. And they typically will be multiples of a given frequency because you have a frequency.
Okay, thank you.
Mm-hmm. What's the major function of an antenna tuner? That's to match an antenna system impedance to the transceiver's output impedance. So again, an antenna tuner matches impedance. Okay.
Does this work in the same way when it's receiving?
Yep. Exactly the same.
Okay.
So the path is reversed. Okay, so now what we're going to say is, what is an antenna? Ideally, if you have a 50 ohm transmitter and 50 ohm cable, which is a conduit to this load, that would be 50 ohms. That means that your signal goes out into the world and never comes back. Okay, so let's say that I'm testing something off the air. I want to still be able to transmit full power. I can replace that 50 ohm thing with a resistor, which is 50 ohms. If I can hook it up to a 50 ohm resistor, is there any difference in my mind between what I'm transmitting into compared to an antenna?
Oh.
I put power out, it never comes back. Well, what ends up happening, this is called a dummy load. And it's used for transmitting off the air and making power tests of your equipment. Now, the important thing to note is that a lot of resistors, especially really big ones, so let's say this is a 1,000 watt dummy load, is built like this. This is a resistor. This is known as a wire wound resistor, and it's typically ceramic and has some cooling fins. Do you see a problem with this?
Looks like an inductor.
It does, because it is an inductor. Well, that's a problem, because an inductor might have a resistance, but it also has an impedance of 2 pi FL. And it turns out that that's a positive impedance. And in particular, it looks like this. And in fact, the overall impedance, we're not getting into this for this class, is actually on the J-axis. So for those of you who do for those of you who've done complex numbers, complex math, it's actually R plus JXL. They're perpendicular to each other. They don't just add. Not only do they do that, they also induce a phase shift. So it's frequency dependent because there's a letter F in there, which means that your 50 ohm resistor is no longer a 50 ohm resistor. And that is why we use a non-inductive dummy load. And typically it's a non-inductive wire wound resistor. That's the basis of our dummy load.
So Scott, if that resistor sort of started acting like an inductor, does that mean that it's, instead of resisting, it's increasing? It's
what it means is that it's
not resisting anymore.
No, it's still resisting, but it's not a reliable 50 ohms anymore.
Okay.
Because I mean, you basically have built yourself a test device, right? You basically built yourself a calibrated test device. If you can't trust your calibrated test device anymore, what is it worth?
Nothing.
There you go.
Okay. So it's doesn't turn into a generator.
No. But it becomes unreliable.
Weird.
It becomes unreliable for the reason you put it together in the first place.
Okay.
Okay, we're now into signals. Yay, signals. Okay, the first one we're going to do is AM, and then there's something called FM. Everyone's heard of AM and FM. AM is the simplest of all the transmitting modes. Okay, what is modulation? Modulation is the modification of some other signal with information to make it look like something and carry the information. Typically, what we do is we take a very high frequency wave. This is usually our radio wave. And we take a much lower frequency thing, such as somebody talking, which is voice. So the radio wave is going to be in megahertz. Our voice is going to be in kilohertz. And we can represent it by looking like this. This is known as a modulation envelope. What we end up with is a signal that then becomes cropped. So the stuff on the top and the stuff on the bottom go away, and we now have a modulated signal inside the red lines. And this is known as amplitude modulation. Okay, or AM. The other thing we can do is something called frequency modulation, where we have the voice or some other signal coming in, and we use that to take this base frequency, and depending on what's happening, we can speed it up or slow it down. And we can speed it up and we can slow it down. Now, it's also true that what we end up looking at in the real world is that most noise that's naturally generated, such as thunderstorms making lightning and things like that, most noise is AM. Most noise is not FM. FM is kind of one of those things that's not a naturally occurring thing. And on top of that, when we get into a radio, when we demodulate it, we kind of cap off the maxima, and we basically just end up with a frequency of a constant amplitude. So if there was a lightning strike, lightning, makes RF noise. If I were to draw the RF spectrum and say this is from 0 to infinity frequency, hertz, lightning basically has a profile that looks like this. It's a pulse and it generates noise across all frequencies equally well. Well, if I'm looking at FM, okay, so what? That basically means that my whole signal for a very short time is just going to be bigger. And by the time I get it into my transmitter, I ignore it anyway, which means that, as they discovered in the 1930s, FM is immune to noise. That's why FM is immune to noise. That's why people like doing FM radio. It's a lot quieter and cleaner than AM radio. Okay, so now what we're going to do is take our frequency spectrum and we're going to start working in the frequency spectrum a lot as opposed to time. What we drew up top, those are time. On the bottom, we're looking at frequency. So how things are spread apart. So here we go. This is our time domain. This is our frequency domain. So our frequency is measured from 0 to infinity hertz. So this is our graph. This is our plane of existence now. So what we're going to draw is our center frequency. And now what we're going to look at is AM. Our AM signal is going to look like this, where we have a spike right in the center on the center frequency. That's known as our carrier frequency. And then we have two sidebands, which you may have heard of before. One is known as the upper, because that's on the upper part of the frequency spectrum. And the other one is known as the lower sideband, or LSB, which is on the lower side of the spectrum. What happens at that point is, okay, well, this is AM. We can now actually say how much bandwidth is taken up by somebody speaking into an AM voice signal. This is about 6 kilohertz. It takes up 6,000 hertz of space on the band. And we're talking physical, virtual space. How much room does it take up? Like if there was another signal that was right here, these would now be interfering with each other because they're overlapping. So we're going to make that other signal go away. And we're also now going to say that the upper and lower sideband are actually mirror images of each other. Well, if they're mirror images, they have the same information. And so I'm going to choose, let's not bother transmitting the lower sideband. And in addition to that, I can always make my own carrier frequency. There's no information in that. So I'm just going to transmit the upper sideband. I'm going to filter everything out before I make it, and I'm just going to transmit the upper sideband. So if my other signal was 6 kilohertz wide, how wide is this one?
3.
That's 3 kilohertz wide. I just saved 50% of the room on the band. What that means is now that other station, which was right there and interfering, is now out of my passband, and I'm out of his passband, and we are not interfering with each other, which means that we basically made better use of the band, which is great. That's exactly what we want. We want to make better use of the spectrum because it's a limited resource. Frequency modulation, the reason that we don't usually use it is because frequency modulation will fill up a space that looks between 10 and 15 kilohertz wide. This is why we use frequency modulation on higher frequencies. If we were to look at some of the lower bands, we would find that 10 to 15 kilohertz is a lot of room. However, if we go up to the 2 meter band, which is 144 to 148 megahertz, we want to rewrite that in kilohertz. It's 144,000 to 148,000 kilohertz. 10 to 15 kilohertz is really no big deal. Fits in there just fine. So FM works really well on the VHF bands and the UHF bands because there's a lot of space available. Okay, so that means that for VHF and UHF, we typically use FM. This that I'm holding, this is an FM handheld radio. This little FRS radio, which is channelized, is also an FM radio. When you listen in your car, that's also FM radio if you're tuned to 98.6 or 98.7 or 97.2 or 97.1 or 100.3 FM. It doesn't indicate the frequency band you're on. It indicates the modulation technique that's being used. VHF packet, because you can send VHF packet over a handheld radio, it's digital communications over FM. So FM is typically used for packet. Packet is, in its purest form, exactly how we are talking to each other over the internet today. That's one of those things that was invented over the radio and has found its way into computers and the internet. The AX.25 protocol. Yeah.
So when we tune to a certain, I guess it's not a frequency number on the FM in the car, what exactly does the number represent?
It's megahertz. Or,
So it is a
or kilohertz if you're on AM.
So it is a frequency.
Yep.
Okay.
You're
And
essentially tuning your eyes, your radio eyes, to a different frequency, different wavelength.
But then you said that we have a certain range of frequencies because of the frequency modulation, right?
Well, basically, the amount of room that it fills, that a single channel fills, for instance, on our version of FM, is between 10 and 15 kilohertz. If we were to look at, the spectrum of commercial band, your broadcast band FM radio, it would actually be about this big.
I'm sorry, it would actually be what?
About this big. That big green swath. Now, that's not obviously from 0 to infinity, but that's actually about 200 kilohertz wide. The reason that we do that is because there's something called deviation. Deviation determines what your voice does to the frequencies. The deviation is much higher for commercial radio. The reason that it is because the greater the deviation, the greater the fidelity that you can reproduce. And because you want to be able to hear classical music as opposed to just somebody talking, it uses much higher deviation, which means it takes up a lot more room.
Okay.
So when you tune into, say, 97.1, you have, what, about 20 kilohertz
200
above and below? 200?
100 kilohertz above and below, which is why if you look at those frequencies, you'll see that there's 97.1, 97.3, 97.5, and you can't tune in between.
Okay.
They're separated by that much for that very reason.
Okay. That makes sense.
To keep from interfering with each other. Okay. Which of the following is a form of amplitude modulation? That would be single sideband. Which type of voice mode is most often used for long distance weak signal work? That is also single sideband. The reason being that FM radio has kind of a nasty habit where if the signal is not particularly strong, it kind of goes away completely. So it's known as the capture effect. It's also true that this is the reason that aircraft still use AM, because on FM, the stronger signal will win by a lot and the weaker signal will disappear, whereas on AM, you'll actually still be able to hear both. So an air traffic controller, if there's somebody else, if there are two stations there, they actually want to be able to hear both stations. And that's why air traffic control still uses AM. Where can single sideband phone be used in bands above 50 megahertz? That can be in at least some portion of all of the bands. Okay, so now what we're going to do is we're going to switch over to the frequency spectrum. Okay, so notice on this chart you have SSB and weak signal, no FM. And notice that there's a little green section on every one of those bands that is isolated just in green that says no FM. And that means no FM. Single sideband only. It means for weak signal work. That's how you do your moon bounce. That's how you do your long distance communications. That's how you do your experimental modes.
What do you mean by weak signal and why?
Weak signal is because let's say you're bouncing signals off the moon. Let's say that you are trying to do point to point and your signals are just barely marginal. Your FM signals will never be heard.
Why do you want the signal to be weak or something like a
You
moon
don't.
bounce?
But let's say you're trying to use a mode where you're trying to make communications over a distance of 1,000 miles using VHF. Your signal is going to be weak, but it might be possible. So, in other words, it's the thing that you're using it for.
So those bands are reserved for weak signal in order to not take over this weak signal.
Well, in other words, if an FM station came into those bands, nobody would be able to hear the weak signals at all. They would completely be swamped.
Okay, thank you.
Mm-hmm. It's again,
Okay,
it's
so
to keep the peace.
What you're saying is it's weak signal by virtue of the fact that it's going so far.
Yeah. Yeah,
So
I mean,
it just
you're
loses
doing it.
over the distance.
You're operating that way on purpose. So, in other words, that area is reserved for the people who are trying to do that.
Right. So I'm trying to go. I'm trying to go 1,000 miles. So by virtue of the fact I'm trying to go that far, my signal is going to be weak.
Yep.
So you can't. So
Everybody
people
else
who have
back
stronger
off.
signals aren't allowed to get in there.
Right. Everybody else back off.
Okay, I got it. I got it.
So it's weak on the receiving side, not on the
Correct.
transmitting side.
Well,
Okay.
it could be both, but usually it's on the receiving side. The advantage of single sideband over FM is that single sideband has a narrower bandwidth. The approximate bandwidth of single sideband is 3 kilohertz. The approximate bandwidth of VHF is between 10 and 15 kilohertz. We are actually also allowed to do fast scan television. Notice this says, amateur TV fast scan. This uses something called NTSC, or the National, I don't remember what it is, Television Standards Code? Can't remember exactly what it means, but it's the US standard. Notice that amateur TV fast scan is this light blue. We're allowed to use it down here on 70 centimeters. We're allowed to use it up here on 900 megahertz. We're allowed to do a whole bunch of different channels. But notice that this goes from 1240 to 1246. That's one channel. That is one TV channel. It takes up 6 megahertz of space. So why don't we do it down here on the 2-meter band? How big is our 2-meter band? It goes from 144 up to 148. How many megahertz is that?
4.
4. It's not even big enough for one single TV channel.
Right.
Right? So, as it turns out, if you think about, most people never thought about the VHF and UHF TV channels, 2 through 6 and 7 through 13, 14 to 83. If you're young enough, you've never seen over-the-air TV like that. Each of those TV channels took up 6 megahertz of bandwidth. So, you think it's probably a good idea that they came up with digital TV. Digital TV saves a lot of bandwidth, which means they could repurpose a lot of that spectrum. So NTSC is the standard by which an analog fast scan. Oh, here we go. National Television Standards Committee, NTSC. That defines the TV picture standard. Okay, we also have a couple of other modes that we like to use. One of them is CW. CW is continuous wave, also known as Morse code. Notice that we have on these bands CW, and there are on the 6-meter and 2-meter bands and 222 to 222.1. It's considered a weak signal mode, but it has a special place. By law, on this band, which is 2 meters, and on this band, which is 6 meters, by law, there is only Morse code allowed in the bottom that little bottom corner of the band. It also has a very narrow bandwidth of about 150 hertz, which means you can pack a lot of Morse code signals side by side on a band and still be able to have people talking. We use something called International Morse. There at one point was something called American Morse. Don't be fooled. American Morse was far inferior to the International Morse code.
You mean we're not exceptional in this
Nope.
respect?
International Morse code. And what's cool about it is that there are actually characters from international alphabets as well, a lot of which I don't know. But like I heard people talking in Swedish on Morse code. You can tell the standard letters, but then there's a whole bunch of things that I don't know, like, A, like a letter A with a little circle over it. That has a special character. What's an electronic keyer? An electronic keyer is a device that assists in the sending of Morse code. Okay, now we're on to digital modes. So we skipped to where it says digital modes, packet, PSK31. You might have a couple of blank pages. I have it as page 46. Depending on the version you have, it might be 44. Does somebody want to confirm that?
Yeah, I have the 2 blank pages. And
Okay, so it'll say 46 in that one.
46, yes.
Okay, digital modes, packet, PSK31, etc. Okay, so a lot of what we do is, believe it or not voice. Ham radio is a lot of different things, and part of it is not voice. We do talk, but we also do a lot of not talking, and we do a lot of digital communications. Digital communications modes include packet radio. Packet is the AX25 protocol. That is what the internet is actually originally built on, believe it or not. There's something called 802.11. That's also known as Wi-Fi. That's IEEE Wi-Fi. And there's something called JT65, which is a mode that was invented by Joe Taylor, Nobel physicist Joe Taylor, K1JT. So we do a lot of digital modes. Okay, so as far as what can be included in packet transmissions. A packet transmission, so what we're going to do is, because we're dealing with digital, what are the 2 numbers that exist in digital, everybody?
0.
0 and 1, that's right. We're talking about just zeros and ones. Okay, zeros and ones are used to send digital information. This is a not, this is no, and this is yes. So, in its simplest form, that's what we would basically have. Okay, so let's say that I wanted to send a word that had 3 different bits, right? So 3 bits, I could send a 000, 001, 010, 011, 100, 101, 110, 111. So if I have 3 bits, I can send 8 different things, or 2 to the 3rd power. So there's that 3, it shows up right there. If I have 10 bits, I can send 2 to the 10th different words, which is about 1024. So what's important here is to say, okay, well, let's say that I send to the other guy, the other person, I send 010. Right? If everything's perfect, what's the other person going to receive?
010.
Okay, perfect, 010. That sounds great. They record it as, this is a number 2. And they would get it as a number 2. But what would happen if somehow in between this channel, which we're sending information through, which is known as the atmosphere or the world or whatever, there is noise on this channel, and they receive this signal as 110. Well, that's a number 6. I sent a 2 and they got a 6. That would be a mistake, would it not? Okay, this is a problem. So what we would do is we would add something called parity, P-A-R-I-T-Y. Parity is our way of adding additional bits that say, okay, what did we send? And we're going to add a couple of additional things to make sure that it gets there on the other end, or at least they know if something's wrong with a high likelihood of success. Okay, so what we're going to do is we're going to add up the number of ones in here. And if it's an odd number, we're going to add a 1. And if it's an even number, we're going to add a 0. All right. Well, we got 1, 1, so we're going to add a 1. So what we're going to send is 01, 01. There's still some static or noise in here, and it gets distorted, and they still have the same problem, and they get 1, 1, 0, 1. Do they have an odd or even number of ones in there?
Odd number.
Odd number. How many did I send? There should always be an even number. So they can look at this and say, no go. That would be called a NAC or a no acknowledge, or basically, I got it wrong. And they would send this NAC packet back and say, please resend.
Okay, Scott, but what if the way it got changed by the noise is to a 100?
So
What you're
let's
saying
say
is it's still
let's say-
negative, so it's not going to know
Yes,
that
okay.
it's wrong.
That's right. And then you start dealing with an acceptable level of errors. Because if it's distorted by that much, then you know you have a big problem. At which point then you say, okay, well, what I'm going to do is maybe I'm going to add another parity bit or another parity bit. So I'm going to add 3 copies of the same thing. And now I have, let's say, 1001111. Okay, and there's some other thing, okay, saying, okay, these have to match, and, well, okay, I still got something that didn't work, so maybe that's not the best way to do it. So maybe there's some other method of encoding it. And then you start basically dealing with more complex methods of encoding. Maybe maybe part of what you do is you duplicate it and then add parity. That would be a 0. And then the other person would get 1000100 or something. And they look at it and say, okay, well, first of all, those don't match. So that's a big problem. And the parity is such that I can't figure out where it is. Okay, that obviously is still bad. But now let's say that I add another parity bit. So basically, by duplicating information and by adding more and more parity bits, especially if you've created it in a way that there's some intelligence where you can actually find out exactly which bit is wrong, that's the difference between error detection and error correction. Sometimes you might actually send it 3 times and say, okay, well, part of your voting on whether it's right or wrong is you get, okay, 3 sets of the same thing. And what if it's 0, 1, 0, 1, 1, 1, 0, 1, 0? Well, I got 2 that matched. That must be the right one. So there's all different methods of doing this. Now, what do you notice about what you sent originally and how much time it took to do it?
The more you have to duplicate, the more time it would take.
Which means that it slows down your data.
Okay.
Exactly right. So digital modes are great to have, and sometimes the amount of error correction and detection that you throw in there determines how much you slow them down. Sometimes it might be worth it, sometimes it might not. If you're sending information to a satellite, it might be really important because if it gets it wrong, the satellite will crash into the ground. You know, if you're sending it to a spacecraft that is like Voyager, that's like on the edge of our sun's impact, you know, and it takes 17 hours for the signals to get there, take as much time as you want. Make sure that it's right. You know, if it's just like sending data across town to each other and you're just talking to a friend about something, No big deal if it's wrong. Okay, so which of the following can be included in packet communications? That would be a checksum, a header that contains the call sign of the station to which the information is being sent, and an automatic repeat request in case of error. ARQ is that automatic repeat request. What is it? Basically, it says, I got it wrong. Something's not right. Please send it again. It's an automatic thing. The reason it's automatic is because packet communications usually happen in an automated fashion. And if anyone's curious, if they have a radio, wherever you are, you can go to 144.390, and very often you'll just hear packet bursts being sent automatically. APRS is the that's a packet burst over FM radio. Did everybody hear that?
Yeah.
That annoying sound?
Yeah.
Okay, that's packet. Instead of voice, it's basically data over your FM radio. Automated packet reporting system, that packet was probably an APRS packet burst. APRS is a hybridized system of radio and GPS, or the global positioning system, and mapping. So you can take a look by going to, for instance, aprs.fi and see that it's loading. And what people basically do is take a radio and a GPS and they'll combine the two, and they'll continually send out, here I am, here I am, here I am, and it's a way of combining. Oh, look, there's somebody who went on a pretty long drive too. It's a way of combining radio with global information systems, and you can use this to track balloons as they fly, or model rockets. You can use it to figure out how fast something is going up or something is going down, because it's based on the global positioning system. So a use of this, providing real-time tactile digital communications in conjunction with a map. That's exactly what we're looking at here.
The GPS would be a different system here that's just paired with radio, right?
I mean, it's a GPS receiver that's just providing location data. And typically it's riding right along with it. Some radios actually have a GPS built in.
Okay. And so like how does the radio integrate with the GPS coordinates here?
Well, that would be the software that somebody writes to mush them all together. To turn them to essentially.
I guess I'm wondering what's GPS. I can assume there's coordinates that are data packets.
Yep.
For the radio, what do you pair with the coordinates?
You basically just say. I mean, you're essentially just including your GPS data in the packet that you're sending out, saying, here I am, and here's my location.
Okay, thank you.
And then that goes to a global server. Somebody puts it on a map. You can show it on the map.
Cool. Thank you.
Yeah. So let's see. What does the abbreviation PSK? PSK means phase shift keying. So we talked about FM. So now we're talking about phase. Okay, does everybody remember from a couple of days ago that we were talking about waves and circles? That might be the best sine wave I've ever drawn. So we're talking about waves and circles, and the fact that a wave has 360 degrees because it came out of us going around a circle. Remember, that was just 2 days ago, everybody. So in order to shift the phase, what we would do is we would basically take this signal and cause an instantaneous jump so that the signal is now moved a certain number of degrees. Or in other words, we would take it and we would move it over here so that the new starting point was over here at 90 degrees. This would be a plus 90 degree shift, and this would be a plus 90 degrees. So phase shift keying is something that we actually take a wave that looks like this, and when something happens to it, we will take it and cause it to jump a certain space so that instead of being here, it will suddenly be up here. Your receiver will see that sudden jump and say, oh, something happened there, and convert that into data. The nice thing about that is that that sudden jump typically causes a very, very small amount, requires a very small amount of bandwidth. So we use a mode called PSK31, for instance. PSK stands for phase shift keying. PSK31 is a mode that requires about 31 hertz of bandwidth. It also is the approximate data rate, which is about 31 characters per second, which is about as fast as somebody can type on the keyboard. Which of the following best describes digital mobile radio? DMR is a method by which we actually time slice a frequency so that two different channels, two different groups of people can use it. So essentially your radio is completely quiet, your radio is completely deaf for half of the time. And because of that, everybody who's using it, their radio is basically deaf for half of the time, which means that two different groups of people can use the exact same frequency and not even know that the other one is there. That's known as a talk group. It's a way for groups of users to share a channel at different times without being heard by the other channel. How do you program it? You program the group's ID code into the radio, and then it knows how to synchronize up to use that slice. Which of the following operating activities is supported by digital mode software in WSJT? Again, that's something that was invented by Joe Taylor. WSJTX. That includes the JT modes, it includes FT modes, and a very fast meteor scatter, MSK. So we do meteor scatter, we do weak signal propagation beacons, and we do moon bounce with these modes. They're very, very, very good at very weak signal operation. FT8 is one of those very popular modes. A lot of people use FT8. It's a very rudimentary mode that operates 15 seconds at a time. Basically, one person's computer will be programmed to say, okay, I'm looking for someone. And then another station will say, hey, I heard you. Here's your signal report. 15 seconds. And then the first person will say, hey, I got you. Here's your signal report. And then that person, the other person will say, hey, I got you. Bye. It's very, 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 very rudimentary communications. There's no voice at all. Some say it's like watching paint dry, but it's a way of communicating that's really good for doing moon bounce, because you're never going to be able to talk to somebody bouncing signals off the moon unless you're running a massive amount of power. This is a way to do some very esoteric modes using a very small amount of power or using very poor conditions. There's also something called broadband hamnet. Hamnet, we have something called ARDN, A-R-E-D-N, and that's basically using commercial Wi-Fi gear modified to be ham radios. And again, if you look up something called ARDN, A-R-E-D-N, you'll find that there's a lot of stuff like that, because the dividing lines these days between ham radio and internet technology, there are a lot of people out there who actually operate their radios from other locations using an internet link. I have been known to operate my station, which is actually outside in the garage, from inside the house, just using TeamViewer to control the screen. All right, so now we're up to electrical safety. Be safe. Power supplies, power circuits, hazardous voltages, and ways to not kill yourself. Okay, what health hazard is presented by electrical current flowing through the body? It can cause injury by heating tissue, it can disrupt the electrical function of cells, or cause involuntary muscle contraction. Please raise your hand if you've ever gotten a 120 volt shock or worse. I am curious.
Yep.
Okay, has anyone ever been hit by 480 volts? Hopefully
Yep.
no. Who said yes?
Me?
Okay, I am really sorry. Did it do a lot of damage?
Threw me across the room.
Did it? Okay. Was that in a motor control center or something?
In a house electrical installation.
Oh, okay. With 480 no less.
I'm in Australia, remember?
Oh, right. Oh, wow. Okay, that's yeah. Right. So your normal voltage is 230. And
Yeah.
it comes in as three phase?
That was only single.
Okay. Well, I've been hit by 250 volts DC. I was 10 years old and I'm lucky to be here today.
Ouch.
Yeah, that was inside a an old vacuum tube transmitter, or actually vacuum tube receiver. I accidentally I had the lid up. I had the cover open and I was sticking my hand inside, which I probably shouldn't have been doing. And I hit something that I shouldn't have, which was the B plus for a vacuum tube operating 250 volts. The next thing I knew, when I was 10 years old, my arm started here and it ended up way up here, and I had no idea how it got there. So I was very lucky that it didn't cause me to grab it. In the United States, what's the green wire in a three wire electrical plug? That's equipment ground. Mark, I assume in Australia it's green and yellow.
Yeah.
Okay. What's a good way to guard against electrical shock? Use three-wire cords, connect all AC-powered station equipment to a common safety ground, and use something called a ground fault interrupter. If you live overseas, it's a residual current device, or RCD. What's the purpose of a fuse? To interrupt power in case of overload. Why should you never put a 20 amp fuse in place of a 5 amp fuse? And that's because the 5 amp fuse will blow and the 20 amp fuse won't, and you could catch something on fire. Safety equipment that should always be included in home built equipment: a fuse or circuit breaker in series with the hot conductor. What type of hazard can exist in a power supply when it's turned off and disconnected? You can receive a shock from the charge in the capacitor. So, funny story. My dad once came home from work with a 500,000 microfarad capacitor from a computer power supply. It was about the size of my adult fist. And I charged it up using a 9-volt battery and said, oh, that was boring. Well, I guess I better discharge it. I took a screwdriver in each terminal of this big capacitor, and I slowly went like this, and as they got close, there was a really, really bright flash and a pow! And I took 2 chrome vanadium screwdrivers that had previously been very nice screwdrivers, and I had a little melted pit on each one. So, what I learned right there is that even a very low voltage can be used for doing something called what?
Welding.
Welding! That's exactly right. That is arc welding. Even a very low voltage. It's all about the current. What is the following? Which of the following is a safety hazard of a 12-volt storage battery? Shorting the terminals can cause burns, fire, or explosion.
Paige, where are you?
I am about to be on the top of 51. What can happen if a lead acid battery is charged or discharged too fast? A lead acid battery has sulfuric acid in it. That sulfuric acid can cause dissociation into hydrogen gas. You can get a spark, which ignites the hydrogen gas. Then, at best, you get a little explosion. At worst, you get an explosion that involves the sulfuric acid, and you get a shower of sulfuric acid all over yourself. So, be careful. Okay, antenna and tower safety. Which of the following is an important safety precaution to observe when putting up a tower? Watch for overhead wires. You have to make sure that any part of any antenna that falls outside of 10 feet of the power wires. Nothing can get anywhere within 10 feet of the wires. Why should you avoid attaching an antenna to a utility pole? First of all, it's not yours. Secondly, you can come in contact with high voltage wires. When I was about 25 years old, I went to a demonstration by Dayton Power and Light at the Dayton Hamvention, where they'd brought 7,200 volts into the building, and they said, "Okay, we're going to hang this sisal rope over this over this wire, over the wire, and see what happens. And nothing happens. He's like, okay, now we're going to wet the rope and stick the other end in a bucket of water on the ground. And then he used his grappling stick and put it there, and it disappeared in a flash. So 7,200 volts can really ruin your day. What can happen if a person touches your antenna while you're transmitting? You could get a very serious RF burn. An RF burn basically goes along and then into your skin and makes a nice little pit in your skin. So don't grab a transmitting antenna. When should members of a tower work team wear a hard hat and safety gloves whenever any work is being done on the tower? A good precaution to observe before climbing a tower is to put on a carefully inspected harness with a fall arrestor, which is basically a springy thing, so that if anything happens, you don't end up going all the way to the ground. And you also don't end up just getting caught and receive a really hard jerk. And safety glasses. When is it safe to climb a tower without a helper or an observer? And the answer is never. Which of the following is an important safety rule to remember when using a crank-up tower? You put your locking devices into the tower, or you crank the tower all the way down before doing any work on it. In its fully extended position, it is designed to handle antennas, not people. The purpose of a safety wire through a turnbuckle used to tension guy lines. Basically, a turnbuckle is like a circle that when you turn it, it tightens both ends of a rope or wire. In wind, it tends to vibrate and it can loosen, and your ropes will and your guy ropes or guy wires will loosen up. So you put you put your safety wire through them, and that keeps it from untwisting. The purpose of a gin pole. A gin pole is basically a portable pulley on a pole. Or, if you want to think of it this way, it's a crane. It's a hand-operated crane that allows you to pull things up to above where you are standing on a tower so that you can easily grapple them. Because there's nothing worse than pulling a 50-pound piece of antenna up and having to, pull just straight up instead of pull down on a rope. When putting up a tower, follow local electrical codes. What is proper grounding for a tower? Separate 8-foot long ground rods for each tower leg bonded to the tower and to each other. Lightning wants to follow the easiest possible path. Which of the following is true when installing grounding conductors used for lightning protection? Avoid sharp bends. Lightning does not like to go around corners. The other thing is never solder anything, because lightning will simply just melt the solder. You want to weld everything or have a nice hard connection. You want to make sure that all your connections are short and direct when installing lightning protection. When it comes to external ground rods for earth connections, you want to bond them together with a heavy wire or conductive strap. And which of the following precautions should be taken when installing devices for lightning protection in a coax cable feed line? So there's something called a transit trap, in case anyone's... Yes, it's 12:01, Izzy. I'm watching the time. There's something called a transit trap, which if it's in coaxial cable, let's say something hits your antenna, the signal comes down through the cable. It will hit this little device, which has a gas-filled tube. It'll ionize the gas and allow the lightning, hopefully, to jump to the outside, and then all your lightning arresters are on a single plate, which then tie to the ground. Hopefully, for those of you who live in the south or in places where you have a lot of thunderstorms, hopefully protecting your equipment from lightning strikes. But what's the most useful thing you can do if you know there's a thunderstorm coming? Disconnect everything. Exactly. All right. So we've got one more page. We've got one more page, and I'm going to do it because we should do it. RF hazards and radiation exposure. VHF and UHF radio signals are non-ionizing radiation, which means they don't have enough energy to cause any genetic damage. They can heat your cells, which is not necessarily a good thing, but they can't cause cancer by going in and messing with the DNA. So they're not like X-rays. They're not like ultraviolet. The maximum power level that an amateur radio station can use at VHF frequencies before an RF exposure evaluation is required is 50 watts PEP. PEP is peak envelope power, which basically means the largest amount of power at any time in your signal can be 50 watts, and then you have to do an evaluation exposure. The easiest way to do it is by actually going to that particular website that I brought up yesterday. And the website is HintLink. And I will actually send this out as part of my recap for today to everybody. Has everybody been getting those, by the way?
Yep.
Yep. Okay, good.
Yep.
So I'm going to, there. Okay, so there's the, okay, so now here's the exposure calculator. You can actually go around and transmit and walk around your area with a field strength meter. You can do computer modeling. I do lots of computer modeling based on antennas that I come up with. The easiest way to do it is just use that calculator and come up with absolute worst case. Duty cycle, if you transmit for half the time and you're turned off for half the time, your duty cycle is 50%. If you're turned on for 10%, and turned off for 90%, your duty cycle is 10%. Duty cycle figures into time averaging of how much power people are exposed to. So, for instance, if your averaging time is 6 minutes, you're transmitting for 3 and turned off for 3, you can actually transmit with twice as much power as the safe limit, because your average is twice as much, and then half the time it's 0. Why do exposure limits vary with frequency? That's because the human body behaves differently at different frequencies of RF, different wavelengths. Our peak absorption occurs at 50 megahertz, which is in the 6 meter band. So our exposure limits are necessarily the lowest at that band. So 50 megahertz is where we peak. What affects RF exposure of people near an amateur station antenna? Frequency and level and power level, distance from the antenna to a person, and the radiation pattern. So if the antenna is pointed that way, how about people over there? Not exposed to a whole lot. Now, if the antenna pattern is omnidirectional in all directions, then it doesn't matter where they're standing. So it's important to know what the pattern looks like. Also, if your antenna is 50 feet up in the air and everybody's on the ground, you're really far from the center of the antenna, and everything's probably okay. So what should you do if your exposure evaluation shows that people are being exposed to dangerous levels? Relocate antennas. It might be putting up a fence. You can also change the time that you're transmitting to make sure that people aren't in that area. Finally, how can you make sure your station stays in compliance with RF safety regs? You evaluate the station whenever a piece of equipment is changed. You change an antenna, you change a piece of feed line, you just go through and do the calculation again. You go back to that website and you do this, and it's all really, really easy. Then you print it out, you calculate your energy densities, and then you print it out and put it up on the wall. And then you're in compliance. And that's it for today. So tomorrow is going to be setting up a station and then how to operate it. And then staying inside the legal limits, making sure you comply with the FCC. So, any questions? Nothing?
Yeah, well, just real quick, what is your exposure of standing under the high voltage transmission towers?
I mean, if you're looking at it as an RF generator, which it is, I mean, more than generating RF, what you could look at it as, like, for instance, when I was a kid, I worked on a golf course. My job was picking the driving range, right? and there were high tension lines running right through the middle of the driving range. It was really fun when you were actually able to hit either one of the wires or the tower with your golf ball, because it made this boom sound. It was really cool. But what I noticed was that if it was misty out and I got under the power lines, I could hear,
Yes.
and I could feel a little bit of like my hair sticking up. There's not RF to worry about because it's 60 hertz. The wavelength is 5 million meters long. Right? It's generating RF, but really what it is the fact that it's at 500,000 volts, and it's let's say 50 meters above or 40 meters above the ground. So you have an electric field of a certain number of volts per meter because the ground is at ground.
Yeah.
So what it is at that point is that, if you were to, let's say, hold up a fluorescent light bulb, it might light up. Remember that? Remember that old trick? My dad and his friends used to do that when one of them was transmitting with his kilowatt transmitter. You could actually hold up a fluorescent light bulb, and it would light up at the same with the same intensity as the guy who was talking. It was an indicator, power indicator.
So does that mean you're getting radiation?
Of course.
Yeah, a lot.
Not necessarily. It doesn't take a lot to fire up a fluorescent light bulb.
You just wouldn't want to stand there too long.
I just wouldn't want to be there too long.
You wouldn't want to live by one of those power stations.
Probably not. But there's still. What the reason that I wouldn't want to is that they generate RF energy even on the ham bands. I wouldn't want to have to deal with the noise.
There's a lot of research on that where people have had all kind of birth defects and animals and everything else that have lived near power lines.
Yeah. I personally wouldn't want to just because, but.
All right. Thanks a lot.
Any other questions? It could be literally anything. Has everybody signed up to take a test? I haven't looked at the roster.
No, what do we need to do to sign up?
Okay, so in the initial packet that I sent out, did everybody get the packet?
Yes.
It had the big zip file, and there was like welcome to radio class or welcome to schools out radio class. At the bottom of that, there is a link that says to sign up for an exam, go to this site. Click here.
Okay.
And if anyone is curious what it looks like this. Let me get this up and share it. Wow, I got a lot of crap email this morning. Look at all that spam. A lot of renewal notices from Norton.
That's not surprising.
That's not surprising. Oh, yeah, I know. I've never actually even had a subscription to Norton. So it's like, interesting.
That's why you're getting the reminders.
Oh yeah, I guess so. Okay, well the site looks like this. And if everybody wants the link, I can do that. I'll put that in the chat. Here's the link. So basically,
That's
this is
35 questions exam.
Yep.
You have 3 hours for the 35 questions?
No, you have as much time as you want. The 3 hours is set up so that everybody can, we're going to cycle through everybody. It really runs from 2 to 5 o'clock, but we'll probably start early and we'll probably end really early. I've had people take as much as an hour and as little as 7 minutes.
Wow.
Yep.
I'm scared to take it.
So Scott, how much of this applies to like a handheld ham radio?
Doesn't matter, does
we're
it?
going.
It depends. It totally
And
depends.
all I need to know is how to use a handheld radio.
Now you sound like me.
Yeah, but see, that's not true. Yes, but then all of a
I'm
sudden
never going to set up a station at my house. I'm
I
never going to have
I
anything
disagree.
bad.
I disagree.
No, I never will.
You
I
cannot.
never, ever will.
You can't say that, right? I guarantee you that you can't say that.
I have
I
too
mean-
many chores and too much desire to be outside. I won't be sitting in my house
Right.
talking to someone from another country on a ham radio. I need a handheld. That's it.
Yeah. Okay. Well, all I can say is you still have to know it all
Mhm.
Oh boy.
because the license covers everything. Now, you don't have to know everything really well.
And then do you have a recommendation on handheld radios in the
I-
$100 range? I was told not to get a super cheap one.
Don't get a super cheap one. Here's
Yep.
okay. You have many options, and this is like here. Let's just go to. So like here's an Icom
All in
V70,
light.
V80. That's fine. Yaesu FT65 is fine. FT8XR is fine. There's the Yaesu again, Linko, DJ VX50. Like, this is a great little handheld that's waterproof, dual band handheld that's waterproof. We bought a bunch of these for the University of Oregon Club. There's, basically
Scott,
there's, yeah.
Those devices, they cover more frequencies than we're allowed to transmit on, right? Or not?
Well,
No.
well, they won't transmit on them. I mean, but like this handheld. It has what commercial band receive. They'll receive a whole bunch of different frequencies. They transmit on the ham bands, but they'll receive a whole bunch of frequencies. This one actually receives AM aircraft frequencies as well as FM radio, like commercial music FM radio. This is this Yaesu FT65 is fine. Basically, there's a whole bunch of absolutely fine radios, and the reason that we picked this one is Alinco's a good brand. It's a nice radio, and this is waterproof.
So like you can communicate on the ham radio frequencies, but also listen to ATC and
Oh yeah, you can listen to all kinds
Okay.
of stuff.
Well,
So I mean, this is this is actually a fairly standard radio that a lot of people in our club have. It's a 20-year-old design. I have 6 of them. It's a dual band, very rugged radio that a lot of people really like. Notice it's $150. You can sometimes find them used for $50 or $60. So, there's a lot of different options.
How come they have such little teeny weeny antennas on?
Because for the most part, you don't need a really big antenna. Now, I also have a 17 or 19-inch antenna that I can take off and unscrew and put that one on, which has a lot better performance. I can also take it and so Jill,
Yeah.
to answer your question, I can almost guarantee that at some point, if you are, let's say you talk to other people, you won't be able to use the radio very well in your car. However, you will probably at some point want to do something like this. And put something like this, on the roof of the car.
I won't be in my car. I'll be on my bike.
You can put this on the bike too. And that works a lot better.
Not.
You say no until you find that that's not true. We have people who actually have put a station on their bike, and then okay, well, what do you combine that with? Well, you have this, and then you have this, right? Then you have a speaker mic, because you find that you don't want to hold the whole radio in your hand, and this has a clip on the back, and you can just clip it right next to your helmet or whatever.
Yeah, I'd like to have one of those with a handheld radio.
There you go.
So, yeah.
So
there's always more stuff that people will sell you that'll help you in whatever ways.
And the other thing is that, and you said you said White River Junction, was it?
Brattleboro.
Where? Oh, Brattleboro.
Yeah.
God, it's pretty up there.
Beautiful.
Yeah. Well, what you'll find is the more that you hang out with your local radio club, the more you'll want, the more you'll realize all this stuff that there is to do, and they'll start, showing you all this cool stuff that you're missing out on.
So in Waco, they have a big bicycle race that they do. And so I've gone and volunteered and helped them there, and it's kind of interesting to do this stuff. And I've gotten a radio, and I've got the real long antenna, but I just got a bio thing.
Mm-hmm.
And they had me add a long antenna, and they programmed it for me, but I haven't got to do anything but listen.
So this past weekend, I missed it because I was sick. We were actually going to go and do it out here in Oregon. We have a lot of really big mountains. They had a 100K mountain bike race up in the woods, and it was through the mud. It used to be called the Cascade Cream Puff, and now it's called the Alpine Epic. And our radio club dragged 20 people up there with a bunch of handheld radios and a bunch of mobile radios on battery power, and provided all the communications for the race.
See, they do that on the Wild Wild West one here, and they rescue a lot of people, and it's a pretty big. I think it's called Wild Wild West. It's a pretty big ride.
And the nice thing about that is that there are a lot of areas where there is no coverage of any other kind. And there are a couple of repeaters up here that people have put up in the mountains that we could, from the aid stations, be able to communicate back and forth from, the aid tents and from the mobile chase vehicle if somebody ends up going and needing help, and back to the base station where they can report. So we were basically reporting health and welfare, the status of all the riders and how they were doing, and they were reporting them back to the main station, the main control station, and putting them up on the board.
I have a question. Like, did they take down all the repeaters in California? Wasn't there some kind of controversy over that, where they were taking down repeaters?
No. Well, what happened in California is, we're going to get into this tomorrow, is in Southern California, if you look at the way the LA basin is laid out, it's basically a big bowl that looks like this, with mountains all around it, and you have like millions and millions of people living in that bowl. And of course, everyone wants to put antennas up on the mountaintops around the city, and around where all the people live. And eventually there were so many people and there's only so many different frequencies that you end up with reuse of frequencies, where this and this repeater, for instance, can both get heard by the same person. This is a problem, because if that person, as we said with FM does not work well with two stations competing. It works very badly, actually. So what they did is that Motorola came up with this thing called CTCSS, where they actually call it PL, where you could basically have this, and the same is true even on this little handheld radio, this little family radio service radio. When they say it has 38 sub channels, those aren't really sub channels. They are PL tones that allow a particular radio to be used on 38 different tones on a given frequency. So that this one might be on 146.76 with a PL of 100.0, and this one is on 146.76 with a PL of 123.0. So that when you're transmitting a particular subtone frequency in hertz, it will only bring up the repeater that is listening on that particular tone.
I thought they were trying to outlaw ham radios in California.
No, they would never do that. Now, there were also repeater wars for this very reason. People would get very possessive of their frequencies, and that's pretty much calmed down. They figured out how to play nice.
Scott,
Yeah.
Is ham radio outlet a good place to buy those devices?
You live in Portland, right?
Yeah.
Take a trip to the candy store. Yeah.
Yeah. Is that the candy store?
That's the candy store.
Okay. Okay.
It's
So,
nice because there's
Scott,
no tax
am
and
I
no
looking
shipping.
for a mobile transceiver? Is that what it would be under?
You want a handheld.
So just a portable?
Yeah.
Transceiver's portable.
Now I also have a mobile radio installed in each of my cars because it's a lot easier to have something, permanently installed.
I have a question. I had bought a CB,
Mm-hmm.
but I didn't get an antenna for it to use in my car on trips. Should I have gotten an antenna?
How would you do it without it?
Magnetic? Huh? I haven't tried it.
Well, I mean, it does. I'm assuming it doesn't have an antenna, right?
It didn't come with an antenna, no.
Well, you need something.
Okay, that's what I was thinking. I need an antenna.
Yeah, I mean that's basically like a 102-inch whip with a mag mount.
What do I need?
It's your typical CB mobile whip antenna. It's like a 102-inch whip.
Okay.
Okay, but now we know why it's a 102-inch whip, don't we?
Why?
But you tell me. If I tell you Citizens Band operates at 27 megahertz, you can tell me why it's a 102-inch whip.
I know I should know.
Well,
I'll give you a hint. It's 11 meters.
It's 11 meters. Yeah.
Divided by 27.2 times the
Yep.
the 39
divided by 27.
Wait a minute, y'all say that again separately.
Here, I'm drawing it. 300
Okay.
divided by 27 is about 11 meters. And we want a quarter wave whip. So a quarter wave of 11 meters is about 2.25. No, 2.75 meters. That would be a quarter wave. And take that times 39.3 inches. And let me grab my calculator just to make sure.
What is that? Right. 2 point what? The second one is 2 point what?
Oh, again, terrible.
2.7.
2.75. It's a quarter of 11. Times 39.3. Oops. 108 inches.
Times 0.95.
Times 0.95 is 102 inches. Really, 102 to 103 inches.
See, I'm not the math person.
Oh, this is the only. I mean, this is one of those things you'll be doing. This is how you figure out. Okay, well there you go. That's why it's a 102-inch whip.
Okay.
So if you don't want something that's going to be 8.5 feet long, I would recommend getting a loaded whip.
A loaded whip?
A loaded whip. So basically, what you'll end up with instead of remember the loading, that's where you basically have a coil at the base.
Yeah.
Okay.
So instead of 102 inches, you're still going to be 102 inches electrically, but you might only be 40 inches tall or something.
Okay. So that would be, yeah.
Yeah. I mean, basically your efficiency would go down a little bit, but so what? It wouldn't be 8.5 feet tall.
If I remember right, Fire Stick was a brand back in the day that had a tunable option that you could adjust the set screw to get your SWR in check.
And Fire Stick, no ground plane, 3-way, 3-foot fiberglass CB antenna. I'm actually looking at one right now.
Well, and about in the 80s, I drove an 18-wheeler, and I know I always had a CB and a whip antenna, but somebody else always did everything for me.
Mm-hmm.
I just talked on it. Or hooked up the coax. That was a long time ago.
Here we go. Wilson CB. Let's see how long this one is. This is 65 inches.
So if I'm
And-
going to Arkansas and I'm driving in the mountains, is that going to be good enough for what I need?
You know, what you get is what you get.
Oh, you put it back up there. I was going to take a picture.
Okay. You know, what you get is what you get. You get what propagation allows you.
So Scott, to buy a handheld, do you need to get the license first?
Nope.
Or
You don't.
No,
you
not
just
with the
buy it?
CD.
No,
And
not
with
with,
the-
not with a ham radio either.
Emergence. I
Yeah,
kind of got
okay.
it.
Oh,
Emergency.
another question here. If I pass the test on Friday, how long will it take me to find out right away? And can I get a vanity call sign?
Okay, to actually have it show up in the FCC database, if it's given by the Anchorage group and the FCC computers are up and working, it could be within an hour, 15 minutes. The vanity call sign is 18 days. Now, the one thing is that you'll also, and this is something I haven't had to experience, basically you'll get a notification from the FCC that you have to pay your $35 your $35 processing fee. It's $15 for the test and $35 for the processing fee. Supposedly that's all worked out now and it's pretty fast, but I don't know exactly how fast.
So we have to pay 15 to take the test
Yep.
and then 35.
35 to the FCC to process it.
And do we just go right after the test on the FCC website and can pay it?
Yeah. That's what I've been told. So notice this right here, this repeater book. So what I'm going to do is, actually, let me hit stop recording.
Oh, yes.
Well, you know, that's okay. I don't mind. There we go.